In a universe containing more stars than grains of sand on every beach on Earth, we sit in absolute silence. Not a single radio signal, not one confirmed visitor, not even a whisper from the cosmic dark. For over 70 years, we've been listening with increasingly sensitive ears, searching with ever more powerful eyes, and yet we remain utterly, inexplicably alone. Most people assume that with trillions of planets scattered across billions of galaxies, alien civilizations must be everywhere. The math seems obvious, even inevitable. But what if our assumptions are catastrophically wrong? What if the silence itself is the answer? This is the Fermi Paradox, the most haunting question in all of science. In a universe that should be teeming with life, where is everybody? Join me as we journey through the cosmic mystery that keeps scientists awake at night, exploring trillion-dollar searches, illusionary discoveries, and theories that will fundamentally change how you see our place in the cosmos. Before we dive into this cosmic mystery, I'm curious, where in the universe are you joining me from today, and what time is it where you are? Drop your location and local time in the comments below. It's fascinating to think that no matter where or when you're watching this, you're participating in humanity's greatest mystery. Picture this. It's a summer day in 1950 at Los Alamos National Laboratory. 4 brilliant physicists are walking to lunch, casually discussing recent UFO sightings in the newspapers. The conversation flows from flying saucers to the possibility of faster-than-light travel, then to the likelihood of alien civilizations. It's the kind of speculative chat that happens when some of the world's smartest minds get together over sandwiches. Then Enrico Fermi, the man who helped build the atomic bomb, a Nobel Prize winner, one of the fathers of nuclear physics, suddenly stops mid-conversation and asks a question that will echo through the corridors of science for decades. But where is everybody? His colleagues knew exactly what he meant. If the universe is as vast and old as we believe, and if life is even remotely common, then our galaxy should be absolutely crawling with alien civilizations. Some of these civilizations should be millions of years older than us. With that kind of head start, they should have colonized the entire galaxy by now. So where are they? Fermi wasn't just making casual conversation. His mind was performing rapid calculations, the kind that made him legendary among physicists. He estimated that even with relatively slow interstellar travel, perhaps just 1% to the speed of light, an advanced civilization could colonize every star system in the Milky Way in roughly 10 million years. That sounds like a long time, but it's barely a blink of an eye in cosmic terms. Our galaxy is over 10 billion years old. This wasn't science fiction speculation. This was cold, hard mathematics colliding with an uncomfortable reality. The numbers suggested that we should be surrounded by evidence of alien intelligence, ancient megastructures, radio transmissions, visits to Earth, something, anything. But Fermi looked around at the vast sky and saw nothing, heard nothing. The universe appeared to be playing an elaborate game of cosmic hide-and-seek, except no one was seeking and everyone was hiding. What made Fermi's question so profound wasn't just its simplicity, but its implications. Either our assumptions about life in the universe are fundamentally wrong, or something is preventing civilizations from becoming detectable. Either possibility is deeply unsettling. The question haunted Fermi for the rest of his life. Colleagues reported that he would return to it again and again, unable to shake the feeling that the universe was keeping a terrible secret. He died in 1954, never knowing that his lunchtime observation would become one of the most important unsolved problems in science. Today, we call it the Fermi Paradox, though Fermi himself never used that term. It's not really a paradox in the classical sense. It's more like a cosmic contradiction. The universe appears to be simultaneously perfect for life and utterly devoid of it. It's as if we discovered a vast library with billions of books, but every single page is blank. To truly grasp the weight of Fermi's question, you need to understand just how alone we appear to be. Imagine standing in a cathedral and hearing your footsteps echo in the vastness. Now multiply that feeling by infinity. Our Milky Way galaxy contains roughly 400 billion stars. Each star is potentially a sun to multiple worlds. Recent discoveries suggest that nearly every star hosts at least one planet. meaning our galaxy alone contains hundreds of billions of worlds. Many of these planets orbit in the habitable zone, that sweet spot where liquid water can exist. But our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. Do the math. We're looking at somewhere between 10 circumflex 22 and 10 circumflex 24 planets in the known universe. That's a trillion worlds. To put this in perspective, if you counted one planet every second, it would take you longer than the current age of the universe to count them all. Among these countless worlds, Earth appears to be the only one producing detectable signs of intelligence. We've been broadcasting radio signals into space for over a century. We've built cities visible from orbit. We've even sent probes beyond our solar system. Yet we've detected nothing comparable coming back at us. This silence becomes even more mysterious when you consider time. The universe is 13.8 billion years old. Earth formed 4.5 billion years ago, and life appeared relatively quickly. Within the first billion years, complex life took longer, but even the most conservative estimates suggest that hundreds of millions of civilizations should have had billions of years to develop before us. Think about human technological progress. In just 70 years, we've gone from the first computers to smartphones, more powerful than the machines that sent us to the moon. In 200 years, we've progressed from the Industrial Revolution to the threshold of artificial intelligence. What could a civilization accomplish with a million-year head start, a billion-year head start? They should be gods to us. Their technology should be as incomprehensible to us as our smartphones would be to ancient Romans. They should have reshaped galaxies, harnessed the power of stars, and left unmistakable signatures across the cosmos. Instead, we see a universe that looks almost entirely natural. No megastructures, no obviously artificial phenomena, no clear signs of cosmic engineering. It's as if we're the first beings in the history of the universe to look up at the stars and wonder if anyone is looking back. The Fermi Paradox isn't just an academic curiosity, it's perhaps the most important question facing humanity today. The answer will fundamentally reshape our understanding of our place in the cosmos, our future as a species, and the very nature of life itself. Consider the possibilities. If we are truly alone, or even just extraordinarily rare, then we bear an almost incomprehensible responsibility. We would be the universe's only known experiment in consciousness, its only hope for understanding itself. Every human life, every piece of art, every scientific discovery would represent something precious beyond measure. The loss of human civilization wouldn't just be a tragedy for us, it would be a cosmic catastrophe, silencing the only voice the universe has ever produced. This perspective transforms everything. Environmental destruction isn't just damaging our planet, it's potentially destroying the only known repository of consciousness in existence. Isn't just human conflict, it's risking the extinction of the universe's only known observers. Our survival becomes not just important to us, but cosmically significant. But perhaps we're not alone. Perhaps the universe is teeming with life, and we simply haven't found it yet. This possibility carries its own profound implications. If civilizations are common but undetectable, it suggests that something prevents them from expanding and making themselves known. That something could be physical limits we haven't discovered, voluntary isolation, or something far more disturbing. The most unsettling possibility is that civilizations regularly destroy themselves before achieving interstellar significance. We've certainly come close. During the Cuban Missile Crisis, we stood at the edge of nuclear annihilation. Climate change now threatens our civilization's stability. If self-destruction is the norm rather than the exception, then the Fermi Paradox becomes a warning, a cosmic cautionary tale written in the silence between the stars. Recent developments make these questions more urgent. We're on the verge of becoming a spacefaring civilization ourselves. Within the next century, we may establish permanent settlements on Mars and begin serious interstellar exploration. We're also developing artificial intelligence that could surpass human capabilities within decades. How we handle these transitions might determine whether we join the Great Silence or break it. The search for extraterrestrial intelligence has intensified dramatically. New telescopes can detect not just planets, but potentially biosignatures, chemical signs of life in distant atmospheres. Radio telescopes scan millions of star systems simultaneously. We're even beginning to look for technosignatures, artificial signals that would indicate technological civilizations. Every null result deepens the mystery. Every silent star system makes the paradox more profound. We're approaching a point where our search capabilities will be so advanced that continued silence would be genuinely shocking. We're closing in on an answer, one way or another. Fermi Paradox also influences our approach to making contact. Should we actively broadcast our presence to the cosmos or maintain radio silence? Some scientists argue that advertising our location could be catastrophically dangerous if hostile civilizations exist. Others contend that if we're truly alone, we have a responsibility to seed life throughout the galaxy. These aren't abstract, philosophical debates. They're practical questions that will shape policy decisions in the coming decades. NASA now officially searches for technosignatures. Major universities host SETI research programs. Breakthrough Listen, funded by tech billionaires, represents the most comprehensive search for alien intelligence ever undertaken. The answer to Fermi's question will also determine humanity's long-term trajectory. If we're alone, we might have a moral obligation to spread life throughout the galaxy, becoming the aliens that other worlds might someday wonder about. If we're not alone, first contact would represent the most significant event in human history, fundamentally altering our science, philosophy, and perhaps our very identity as a species. Perhaps most importantly, the Fermi Paradox forces us to confront the possibility that intelligence and technology don't guarantee survival. The silence might be telling us something crucial about the nature of advanced civilizations, that they face challenges we haven't yet imagined, make choices we haven't yet considered, or encounter barriers we haven't yet discovered. As we stand at the threshold of becoming a truly spacefaring species, Fermi's question becomes our question. Will we break the great silence, or will we join it? The answer may depend on choices we make in the next few decades. Choices about our technology, our environment, and our future among the stars. Before we can understand why we might be alone, we need to appreciate just how perfect our cosmic neighborhood is for life. The Milky Way isn't just any galaxy. It's a rare type of spiral galaxy with conditions that seem almost tailor-made for the emergence of complex organisms. Imagine the galaxy as a vast city. Like any city, it has good neighborhoods and bad neighborhoods. We happen to live in the cosmic equivalent of a quiet suburban street, far enough from downtown to avoid the chaos, but close enough to benefit from the infrastructure. Our location is what astronomers call the galactic habitable zone, or the Goldilocks zone of our galaxy. We're positioned about 26,000 light-years from the galactic center, roughly 2/3 of the way out from the core. This might seem arbitrary, but it's actually the sweet spot for life. Too close to the galactic center, and we'd be bombarded by deadly radiation from the supermassive black hole at the galaxy's heart. The stellar density there is so high that gravitational interactions would constantly disrupt planetary orbits. Massive stars would explode as supernovas so frequently that any developing life would be sterilized by gamma rays. It's a beautiful, violent place, but utterly hostile to biology. Too far out, and we'd be in the galactic equivalent of a desert. The outer regions of the galaxy are metal poor, meaning they lack the heavy elements necessary for rocky planets and complex chemistry. You need elements like carbon, oxygen, silicon, and iron to build planets and life. These elements are forged in the hearts of massive stars and distributed through supernova explosions. The galactic suburbs have just enough stellar recycling to provide the raw materials for life, but not so much that the radiation becomes lethal. But our galaxy structure offers another crucial advantage: stability. Spiral galaxies, like the Milky Way, maintain their elegant arm patterns through density waves, regions where matter gets compressed as it orbits the galactic center. These spiral arms are stellar nurseries where new stars are born, but they're also regions of intense radiation and gravitational chaos. Here's the remarkable part. Our solar system appears to orbit the galaxy at just the right speed to avoid spending too much time in these dangerous spiral arms. We surf between the arms, occasionally passing through them but never lingering long enough to be sterilized. It's like driving on a highway, where every few million years you have to merge through a construction zone, dangerous but manageable if you time it right. Even our galaxy's size is fortuitous. The Milky Way is large enough to have produced sufficient heavy elements through generations of stellar death and rebirth, whole but not so large that it's dominated by the violent processes that characterize giant elliptical galaxies. Those galactic monsters are often the products of catastrophic mergers that would disrupt any stable planetary systems. Our galaxy also has a relatively quiet recent history. We haven't suffered a major merger with another large galaxy in billions of years. Such events scramble stellar orbits and can eject entire solar systems into the intergalactic void. The Milky Way's peaceful suburban existence has allowed solar systems like ours to maintain stable orbits for the billions of years necessary for complex life to evolve. Even the galaxy's magnetic field plays a crucial role. This invisible shield helps deflect some of the high-energy cosmic rays that would otherwise sterilize planetary surfaces. It's like living under a protective dome that filters out the worst of the galaxy's radiation. The Milky Way's spiral structure also regulates star formation in ways that benefit life. Unlike irregular galaxies, where star formation happens in chaotic bursts, spiral galaxies maintain steady, controlled stellar nurseries. This means a relatively constant supply of heavy elements without overwhelming bursts of sterilizing radiation. Consider the alternative galactic environments. Elliptical galaxies are largely devoid of the gas and dust needed for ongoing star formation. They're cosmic retirement communities, where the stellar population ages without replacement. Irregular galaxies experience chaotic star formation that creates unpredictable radiation environments. Active galaxies host supermassive black holes that spray deadly jets of particles across millions of light years. We won the cosmic lottery by being born in a stable, middle-aged spiral galaxy during a quiet period in its evolution. But if galaxy-scale habitability is this restrictive, it raises profound questions about the Fermi Paradox. Maybe suitable galaxies are rarer than we thought. Maybe most of the universe's star-forming regions are too hostile for life to gain a foothold. Yet, even if only 1% of galaxies are as hospitable as the Milky Way, that still leaves tens of billions of life-friendly galaxies in the observable universe. Our galactic good fortune doesn't solve Fermi's paradox. It might actually make it more mysterious. If our galaxy provides the neighborhood, then stars provide the houses. And not just any star will do. The recipe for a life-supporting stellar system requires a precise combination of ingredients that we're only beginning to fully appreciate. Our Sun represents the cosmic equivalent of winning the lottery. It's a G-type main sequence star, a yellow dwarf that burns steadily for about 10 billion years. This might seem unremarkable, but G-type stars represent only about 7% of all stars in the galaxy. 7% of all stars in the galaxy. The vast majority of stars are red dwarfs, smaller, cooler, and potentially problematic for life. Red dwarfs burn for trillions of years, which seems like an advantage for life, but they're also prone to violent flares that can strip away planetary atmospheres. Any planet close enough to receive adequate warmth from a red dwarf would be tidally locked, with one side in permanent daylight and the other in eternal darkness. While life might still be possible in these systems, the stable, temperate conditions we know on Earth would be impossible. At the other extreme, massive blue and white stars burn hot and die young, often in just a few million years. That's nowhere near enough time for complex life to evolve. These stellar giants also emit dangerous levels of ultraviolet radiation that would sterilize nearby planets. Our Sun hits the sweet spot. It's massive enough to burn steadily for billions of years, but not so massive that it burns out quickly or floods its surroundings with lethal radiation. It's also remarkably stable. While all stars experience some variability, the Sun's output has remained relatively constant throughout Earth's history. This stellar steadiness has allowed our planet's climate to remain within habitable bounds for billions of years. But even the perfect star isn't enough. You also need the right kind of planetary system. Our solar system's architecture appears to be carefully orchestrated for habitability. Jupiter, our massive outer planet, acts as a cosmic vacuum cleaner, using its powerful gravity to deflect or capture comets and asteroids that might otherwise bombard the inner planets. Without Jupiter's protection, Earth would suffer catastrophic impacts so frequently that complex life might never have time to evolve. Saturn contributes too, helping to stabilize the orbital dynamics of the outer solar system. The ice giants, Uranus and Neptune, patrol the further reaches, mopping up debris that escapes Jupiter's gravitational influence. It's like having a series of bodyguards protecting Earth from cosmic threats. The spacing of planets in our solar system also appears to be crucial. Computer simulations suggest that small changes in planetary positions could destabilize the entire system. If Jupiter were significantly closer to the Sun, its gravitational influence might prevent Earth-like planets from forming in the habitable zone. If it were much farther out, it wouldn't provide adequate protection from asteroids and comets. Even Earth's moon plays a vital role in our planet's habitability. The moon is unusually large relative to Earth, so large that some astronomers consider the Earth-Moon system a double planet rather than a traditional planet-satellite pair. This oversized moon stabilizes Earth's axial tilt, preventing dramatic climate swings that would occur if our planet wobbled chaotically as it orbits the Sun. The moon also drives our tides, which may have been crucial for life's transition from sea to land. The regular cycle of wet and dry conditions in tidal zones could have provided the evolutionary pressure and opportunity for early organisms to develop the ability to survive on land. Our solar system also formed at the right time in galactic history. Earlier generations of stars hadn't produced enough heavy elements to form rocky planets. Later generations might face different challenges. As the galaxy continues to evolve, we're part of what astronomers call Generation I of potentially habitable star systems, old enough to benefit from stellar recycling, but young enough to avoid whatever cosmic dangers might emerge in the future. So, the very process of planetary formation in our system seems to have been unusually conducive to habitability. The Grand Tack model suggests that Jupiter migrated inward toward the Sun early in the solar system's history, then reversed course and moved back outward. This gravitational dance would have cleared out much of the inner solar system's debris, while still allowing small, rocky planets to form in the habitable zone. Even the timing of major impacts appears to have been fortuitous. The collision that likely formed the Moon happened early enough that Earth could recover and develop a stable crust, but late enough that the planet had already differentiated into core, mantle, and crust. The late heavy bombardment ended just as conditions became suitable for life, almost as if the cosmos was clearing the stage for biology's grand entrance. Our star system also lacks some of the features that could make life difficult. We don't have a close stellar companion that could disrupt planetary orbits. We're not part of a dense star cluster where gravitational interactions could strip away planets. We don't orbit a pulsar or other exotic stellar remnant that would bathe us in deadly radiation. The chemical composition of our solar system is also suspiciously perfect for life. We have just enough water to cover most of our planet's surface, but not so much that Earth became a water world with no land masses. We have sufficient carbon for complex organic chemistry, but not so much that we suffered a runaway greenhouse effect like Venus. Yet here's the paradox. While each of these conditions might be individually rare, the sheer number of star systems in the galaxy suggests that millions of worlds should still meet all these criteria. If 1 in a million star systems produces a perfect Earth analog, the Milky Way should still host hundreds of thousands of habitable worlds. The more we understand about what makes our solar system special, the more mysterious our cosmic solitude becomes. Either Earth-like conditions are far rarer than we imagine, or something else is preventing life from becoming detectable across interstellar distances. Having the right galaxy and the right star system is just the beginning. The final step in creating a cradle for life requires a planet that can maintain stable, hospitable conditions for billions of years. Earth's ability to do this depends on a delicate balance of factors that we're only beginning to fully appreciate. Consider Earth's atmosphere, a razor-thin shell of gas that makes all the difference between a living world and a dead rock. Our atmosphere is roughly 78% nitrogen and 21% oxygen, with trace amounts of other gases, including the carbon dioxide that drives our greenhouse effect. This mixture seems normal to us, but it's actually extraordinary. Oxygen is highly reactive. In most cosmic environments, it quickly combines with other elements and disappears. The only reason our atmosphere contains so much oxygen is that life itself produces it faster than chemical reactions can consume it. For over 2 billion years, photosynthetic organisms have been splitting water molecules and releasing oxygen as waste. We literally breathe the refuse of ancient bacteria. But oxygen alone would be deadly. Pure oxygen is so reactive, it would cause everything to burst into flames. Nitrogen serves as a crucial diluent, making our atmosphere stable enough for complex chemistry, while maintaining enough oxygen for animal respiration. This balance is maintained by the global nitrogen cycle, a complex interplay of biological and geological processes. Earth's magnetic field provides another crucial shield, generated by electrical currents in our planet's molten iron core. This invisible barrier deflects the solar wind, a stream of charged particles that would otherwise strip away our atmosphere. Mars likely lost much of its atmosphere this way, after its magnetic field weakened billions of years ago. The strength of Earth's magnetic field depends on the continued circulation of our liquid outer core, which in turn depends on heat generated by radioactive decay deep within the planet. Too little radioactivity, and the core would freeze solid, killing the magnetic field. Too much, and our planet would be volcanically active beyond the point of habitability. Plate tectonics adds another layer of complexity to Earth's habitability. The slow movement of continental plates serves as a global thermostat, regulating our planet's temperature through the carbon cycle. When the climate becomes too warm, increased rainfall weathering rocks and draws carbon dioxide out of the atmosphere. When it becomes too cold, reduced weathering allows volcanic emissions to build up atmospheric carbon dioxide, strengthening the greenhouse effect. This geological thermostat has kept Earth's surface temperature within the narrow range suitable for liquid water for over 3 billion years, despite the fact that the sun has grown about 30% brighter during that time. It's an incredibly delicate balance. If plate tectonics had been significantly faster or slower, our climate would have spiraled into either a snowball Earth or a runaway greenhouse. Even Earth's size appears to be optimal. A smaller planet couldn't maintain plate tectonics or retain a substantial atmosphere. A larger planet might have such strong gravity that its atmosphere becomes too dense and hot for life, or its increased geological activity might make the surface uninhabitable. Our planet's rotation rate also matters. Earth's 24-hour day creates a moderate climate by preventing extreme temperature differences between day and night. A much slower rotation would lead to scorching days and freezing nights. A much faster rotation would create violent weather patterns driven by extreme Coriolis effects. The amount of water on Earth seems perfectly calibrated too, enough to create oceans that moderate our climate and provide a medium for life, but not so much that the entire surface is covered, preventing the land-sea interactions that drive many crucial geochemical cycles. All these factors work together to create what scientists call the Goldilocks conditions. Not too hot, not too cold, not too dry, not too wet, but just right for life as we know it. The remarkable thing is how stable these conditions have remained throughout Earth's history, despite massive changes like the rise of oxygen, ice ages, and mass extinctions. Yet, if planets like Earth are so finely tuned for life, why haven't we found evidence of biology elsewhere? The growing catalogue of exoplanets includes many worlds in their star's habitable zone, but we haven't yet detected clear biosignatures from any of them. This makes the Fermi Paradox even more puzzling. If the universe can produce Goldilocks planets, where are all the bears? When you look up at the night sky from a dark location, you can see about 2,500 individual stars with the naked eye. That's already an overwhelming number to contemplate, each one potentially hosting its own family of worlds. But those visible stars represent less than 0.0000001% of the stars in our galaxy alone. The true scale of the cosmic census defies human comprehension. The Milky Way contains an estimated 400 billion stars, give or take 100 billion. To put this in perspective, if you counted one star per second, it would take you over 12,000 years to count them all, and that's assuming you never stopped to eat, sleep, or rest. But how do we even count stars we can't see? Astronomers use a combination of techniques that read like science fiction. They measure the total light output of our galaxy and divide by the average brightness of different types of stars. They study the orbital motion of stars and gas clouds to estimate the galaxy's total mass, then subtract the dark matter component. They observe distant galaxies similar to our own and assume similar stellar populations. Each method has uncertainties, but they all converge on that mind-bending number, roughly 400 billion stars in our cosmic neighborhood. And recent surveys suggest that nearly all of these stars host at least one planet. The Kepler Space Telescope, during its remarkable mission, discovered that planetary systems are the rule rather than the exception. This revelation fundamentally changed how we think about the cosmos. A generation ago, we weren't even certain that planets existed around other stars. Now we know that planets are as common as stars themselves, meaning our galaxy contains hundreds of billions of worlds. But our galaxy is just one of many. The Hubble Space Telescope's deep field observations revealed galaxies scattered across space like islands in an infinite ocean. Recent estimates suggest there are approximately 2 trillion galaxies in the observable universe. 2 trillion, a number so large that if each galaxy were a grain of sand, they would fill an Olympic swimming pool. Not all galaxies are created equal. Dwarf galaxies might contain only a few billion stars, while giant ellipticals can host over 1 trillion. But even conservative estimates suggest an average of 100 billion stars per galaxy. Do the math. 2 trillion galaxies times 100 billion stars equals 2 galaxy. Circumflex 23 stars in the observable universe. That's 200 sextillion stars. If each star hosts an average of just one planet, we're looking at more planets than there are grains of sand on all the beaches of Earth, multiplied by 1 billion. Recent discoveries have made these numbers even more staggering. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of which orbit in the habitable zone. Proxima Centauri, our nearest stellar neighbor, hosts at least one potentially habitable world. The K2 mission and TESS transiting exoplanet survey satellite continue to discover new worlds at an accelerating pace. We've also learned that planets can exist in environments we never expected. Or some orbit binary star systems, like the desert world of Tatooine from Star Wars. Others are rogue planets that wander through interstellar space without a star. We've found planets around pulsars, the ultra-dense remnants of exploded stars. The universe, it seems, is incredibly creative at forming worlds. These discoveries haven't just given us a census of planets. They've revealed the incredible diversity of possible worlds. Hot Jupiters orbit their stars in just a few days. Super-Earths, planets larger than our world but smaller than Neptune, appear to be the most common type of planet in the galaxy, even though our solar system doesn't contain any. Each new discovery makes Fermi's question more pressing. With hundreds of billions of potentially habitable worlds in our galaxy alone, and countless more in the billions of other galaxies, the universe should be absolutely teeming with life. The numbers are so overwhelming that even the most pessimistic estimates of life's rarity still predict millions of inhabited worlds. Yet when we look out into this vast cosmos filled with countless worlds, we see no clear signs of life anywhere. No radio signals, no obviously artificial structures, no visitors, just an endless expanse of apparently sterile space. The bigger the numbers get, the more mysterious our solitude becomes. In 1961, astronomer Frank Drake did something that would define the search for extraterrestrial intelligence for decades to come. Preparing for the first scientific conference on SETI, he needed a way to structure the discussion about the likelihood of alien civilizations. So he wrote an equation on a chalkboard, a simple mathematical framework that would become one of the most famous formulas in science. The Drake equation breaks down the question, how many alien civilizations exist, into manageable pieces. It looks deceptively simple. Near equals sign or asterisk. Could be what be if l. But behind each symbol lies a universe of complexity and uncertainty. Let's walk through each term and see how our understanding has evolved over the past 60 years. Risk represents the rate of star formation in our galaxy. This seemed like the easiest parameter to estimate in Drake's time, and it remains one of the most reliable current observations. Suggests that about 7 new stars form in the Milky Way each year. That might not sound like much, but over the galaxy's 10 billion year history, it adds up to our current stellar population. FP is the fraction of stars that have planets. In 1961, this was pure speculation. We had no confirmed exoplanets and no reliable way to detect them. Drake optimistically guessed that perhaps half of all stars had planetary systems. Today, thanks to missions like Kepler and TESS, we know that nearly every star has at least one planet. Drake's optimism was actually conservative. FEP appears to be close to 1.0. NEN represents the number of planets per star system that could potentially support life. This is where things get tricky. We now know that our solar system, with 4 rocky inner planets, is just one possible architecture. Some systems have hot Jupiters that migrated inward, potentially destroying any Earth-like worlds. Others have super-Earths that might be even better for life than our planet. Current estimates suggest that 10 to 20% of Sun-like stars have at least one planet in the habitable zone. Then we hit the biological terms, where uncertainty explodes exponentially. FL is the fraction of suitable planets where life actually emerges. This is where Drake's equation becomes more philosophy than science. We have exactly one data point, Earth. Life appeared on our planet relatively quickly after conditions became suitable, which suggests that the emergence of simple life might be common. But we don't know if Earth represents a typical case or an extraordinary exception. Some scientists argue that life's rapid emergence on Earth indicates it's easy, that given the right conditions, chemistry naturally evolves toward biology. Others point out that we're subject to observation bias. We exist, so we naturally find ourselves on a planet where life emerged. The planets where life didn't emerge aren't being observed by anyone. Recent discoveries have made this term even more uncertain. We've found life in environments previously thought impossible, in boiling hot springs, in ice-covered lakes, in rocks miles beneath the surface. This extremophile life has expanded our definition of habitable conditions, but we've also learned that the transition from non-living chemistry to living biology might require a series of incredibly unlikely coincidences. Phi represents the fraction of life-bearing planets where intelligence evolves. This is where the equation becomes deeply uncomfortable for scientists. Intelligence, as we understand it, required billions of years to emerge on Earth. For most of our planet's history, life consisted entirely of single-celled organisms. Complex cells didn't appear until about 2 billion years ago. Multicellular life is only about 1 billion years old. Intelligence, if we date it to the emergence of humans, is only a few million years old. This suggests that intelligence might be extraordinarily rare. Earth has hosted billions of species over its history, but only one has developed technology capable of interstellar communication. We might be the product of an incredibly unlikely evolutionary accident. FC is the fraction of intelligent civilizations that develop technology detectable across interstellar distances. Even if intelligence is common, technological civilization might not be. Human civilization has only been detectable from space for about a century, a blink of an eye in cosmic terms. Many intelligent species might never develop radio astronomy, space travel, or other technologies that would make them visible to distant observers. Finally, LEV represents the length of time such civilizations remain detectable. This might be the most crucial and terrifying parameter in the equation. How long do technological civilizations last before they destroy themselves, lose interest in broadcasting, transcend into something unrecognizable? If civilizations typically last only a few centuries after developing detectable technology, then even if intelligence is common, very few civilizations would be active at any given time. The galaxy might be full of the ruins of dead civilizations, with new ones constantly emerging and vanishing like fireflies in the night. When Drake first presented his equation in 1961, the assembled scientists made optimistic guesses for each parameter and concluded that thousands of detectable civilizations might exist in our galaxy. They expected that SETI would succeed within a few decades. 60 years later, we've refined our estimates for the astronomical and physical parameters, but the biological and sociological terms remain almost pure guesswork. Depending on your assumptions, the Drake equation predicts anything from millions of active civilizations to the possibility that we're utterly alone. This wide range of predictions highlights both the equation's strength and its weakness. It provides a useful framework for thinking about the problem, but it can't give us a definitive answer. Each parameter encompasses vast unknowns about biology, evolution, and the behavior of intelligent species. Modern variations of the Drake equation include additional terms for factors like the importance of large moons, the role of plate tectonics, and the likelihood of mass extinctions. Some scientists have proposed entirely different approaches, focusing on the probability of key evolutionary transitions or the sustainability of technological civilizations. The equation remains valuable, not because it provides answers, but because it forces us to confront our ignorance. Every term represents a profound question about life, intelligence, and the nature of civilizations. Until we have more data, whether from SETI discoveries, signs of life in our solar system, or better understanding of evolutionary biology, the Drake equation will continue to reflect our hopes and fears about our place in the cosmos, rather than providing scientific certainty. The numbers are so staggering, they almost lose meaning. Conservative estimates suggest that our galaxy alone contains over 40 billion planets in the habitable zones of their stars. But when we expand our view to the entire observable universe, we're looking at planets numbering in the trillions upon trillions, more worlds than human language has adequate words to describe. Let's try to wrap our minds around what this really means. Imagine that life emerges on only one planet out of every billion suitable candidates. That would still leave us with tens of millions of inhabited worlds in the Milky Way alone. Make the odds even more pessimistic. Say that life appears on only one planet out of every trillion suitable worlds. We'd still expect hundreds of thousands of living planets in our cosmic neighborhood. Now, factor in time. The universe is 13.8 billion years old, and the first potentially habitable planets formed over 12 billion years ago. Earth is actually a relatively young world in cosmic terms. This means that many civilizations, if they exist, have had billions of additional years to develop beyond our current level of technology. Consider what we've accomplished in just the past century. In 1923, we didn't even know that other galaxies existed. Today, we can detect planets orbiting stars thousands of light years away and analyze their atmospheric compositions. We've sent probes to every planet in our solar system and landed rovers on Mars. We've built artificial intelligence systems that can process information faster than entire civilizations could just decades ago. Now imagine a civilization with a 1,000,000-year head start, or 10 million years, or 1 billion. They should have capabilities that would seem like magic to us. They might harness the entire energy output of their star using megastructures like Dyson spheres. They could reshape matter at the molecular level, terraform entire worlds, or even move planets to more suitable orbits. Such advanced civilizations should leave unmistakable signatures across the cosmos. We should see evidence of stellar engineering, detectably artificial radio emissions, or obviously constructed megastructures. Even if they're trying to stay hidden, civilizations millions of years ahead of us should find it difficult to mask all evidence of their existence. The Kepler mission alone discovered over 4,000 confirmed exoplanets and identified thousands more candidates. But Kepler only surveyed a tiny fraction of our galaxy, roughly 150,000 stars out of 400 billion. It's like examining a single drop of ocean water and trying to understand all marine life. The full catalogue of worlds in our galaxy is almost certainly far richer than we can currently imagine. Recent discoveries have only made the numbers more mind-boggling. The TRAPPIST-1 system contains 7 Earth-sized worlds, with 3 potentially habitable. Proxima Centauri b orbits the nearest star to our Sun. Kepler 452b is so Earth-like that scientists call it Earth's cousin. 2I 715b is a super-Earth in the habitable zone of a nearby red dwarf star. Each new discovery expands our understanding of where life might exist. We've found planets orbiting binary stars, worlds with exotic atmospheres, and even planets that might be entirely covered by oceans. The universe appears to be incredibly creative at producing environments where life could potentially flourish. But perhaps the most profound realization is how ordinary our solar system appears to be. We're not located in a special place in the galaxy. Our Sun is a common type of star. Earth orbits at a typical distance for a rocky planet. By every measure we can apply, we seem to inhabit a completely average cosmic environment. This ordinariness has profound implications for the Fermi Paradox. If life can emerge in an average place like our solar system, it should be able to emerge almost anywhere in the galaxy. The sheer number of available worlds makes the absence of detectable alien civilizations increasingly mysterious. Some scientists have tried to resolve this by arguing that Earth-like conditions are far rarer than we assume. Maybe our planet's large moon is essential for stabilizing climate. Maybe plate tectonics is necessary for maintaining habitability over geological time. Maybe Jupiter's gravitational protection from asteroids and comets is crucial for allowing complex life to evolve. But even if we accept all these constraints, the numbers remain overwhelming. If only one star system in a million produces an Earth-like world, our galaxy would still contain hundreds of thousands of potential cradles for life. And we've discovered that many of these potentially crucial features, large moons, geological activity, protective gas giants, are actually quite common among planetary systems.
Pause. Outdoors. Observe. Outdoors. 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 Outdoors.
The trillion worlds of the galaxy represent a trillion opportunities for the universe to experiment with biology, intelligence, and civilization. There are a trillion chances for chemistry to become biochemistry, for biochemistry to become life, and for life to become aware of itself and reach for the stars. Yet, when we survey this vast cosmic laboratory, we find no clear evidence that any of these experiments have succeeded, except our own. The silence is so profound, so complete, that it forces us to question our most basic assumptions about life, intelligence, and our place in the cosmos. With a trillion worlds and billions of years, how can we possibly be alone? The story of life on Earth reads like the most improbable adventure novel ever written, from lifeless chemistry to thinking beings capable of pondering their own existence. The journey spans nearly 4 billion years and includes plot twists so unlikely that if you encountered them in fiction, you'd dismiss them as impossible. It begins in what scientists call the primordial soup, early Earth's oceans filled with organic molecules, lightning, volcanic activity, and ultraviolet radiation from an unfiltered sun drove complex chemical reactions in this ancient brew. Somewhere, somehow, these reactions crossed the invisible line between chemistry and biology. Non-living molecules organized themselves into the first primitive cells. This transition, called abiogenesis, remains one of science's greatest mysteries. We know it happened because we're here, but we don't fully understand how. The gap between the most complex non-living chemical systems and the simplest living cells is enormous. Even the most basic life forms require sophisticated molecular machinery to replicate, metabolize, and maintain themselves. Consider what had to happen for life to emerge. Random chemical reactions had to produce self-replicating molecules, essentially chemicals that could make copies of themselves. These molecules had to develop the ability to evolve, to change and improve over time. They needed to acquire metabolism, the ability to harvest energy from their environment, and they had to enclose themselves in protective membranes, creating the first cells. Each of these steps seems individually unlikely. The probability of them all occurring in sequence, on the same world, within a reasonable timeframe, approaches the miraculous. Yet it happened on Earth, apparently quite early in our planet's history. Life appeared on Earth almost as soon as conditions became suitable, perhaps as early as 4.1 billion years ago, just a few 100 million years after our planet's formation. This rapid emergence suggests that either life is easy to create under the right conditions, or Earth got extraordinarily lucky. But the real adventure was just beginning. For the next 2 billion years, life remained simple, single-celled organisms that looked virtually identical to each other. This period, called the Archean Eon, saw little apparent progress. Life existed, but it was primitive, microscopic, and seemingly stuck in an evolutionary rut. Then came the first major revolution, the invention of photosynthesis. Some bacteria learned to harvest energy directly from sunlight, splitting water molecules and releasing oxygen as a waste product. This seems beneficial, but it actually created the first global environmental catastrophe. Oxygen was poison to most existing life forms. The Great Oxidation Event, beginning around 2.5 billion years ago, killed off most of Earth's original inhabitants. But crisis became opportunity. Organisms that survived learned to use oxygen for more efficient metabolism. They developed complex internal structures, organelles, that allowed them to become larger and more sophisticated. The first eukaryotic cells appeared around 2 billion years ago, setting the stage for everything that would follow. Yet even this advance led to another billion-year period of apparent stagnation. Complex cells existed, but they remained mostly single-celled. The leap to multicellular life took another billion years to accomplish. When it finally happened, around 600 million years ago, it triggered an explosion of innovation. The Cambrian explosion, beginning around 540 million years ago, saw the rapid emergence of most major animal body plans. In just a few million years, an eye blink in evolutionary terms, life invented eyes, shells, predation, complex behavior, and sophisticated ecosystems. It was as if evolution suddenly shifted into overdrive after billions of years of careful preparation. From there, life conquered every available environment on Earth. It moved from sea to land, from ground to air, from hot springs to ice sheets. It survived 5 major mass extinctions, each time bouncing back with new innovations and increased complexity. But perhaps the most remarkable transition was the emergence of intelligence. For most of Earth's history, life was driven entirely by instinct and programmed behavior. The development of brains capable of learning, reasoning, and ultimately self-awareness represents one of evolution's most profound achievements. Human intelligence appears to be genuinely unprecedented on Earth. While many animals show remarkable cognitive abilities, none have developed cumulative culture, the ability to build knowledge across generations and fundamentally alter their environment through technology. We're the first species on Earth to understand evolution itself, to manipulate matter at the molecular level, and to contemplate our own existence. This 4 billion-year journey from chemistry to consciousness involved countless unlikely transitions, narrow escapes from extinction, and evolutionary innovations that each seem individually improbable. The human brain, with its 86 billion neurons forming trillions of connections, is arguably the most complex structure we know of in the universe. Yet, if life's journey on Earth represents a typical path from chemistry to consciousness, then intelligence should have emerged on countless worlds throughout the cosmos. The fact that we don't see evidence of other intelligent species forces us to confront uncomfortable possibilities. Either we're extraordinarily lucky, or there are barriers along life's path that are far more formidable than they appear from our singular perspective. The story of life on Earth is simultaneously inspiring and terrifying. It shows that the universe can create conscious beings capable of wonder, love, art, and scientific understanding. But it also suggests that the path to intelligence might be so narrow, so fraught with catastrophic risks, that most attempts fail before reaching their destination. Imagine life as a cosmic obstacle course, with multiple challenging barriers that must be overcome for simple chemistry to evolve into a spacefaring civilization. Somewhere along this course lies a nearly insurmountable obstacle, a great filter that prevents most potential life from advancing beyond a certain point. This concept, popularized by economist Robin Hanson, offers one of the most compelling explanations for the Fermi Paradox, but it comes with terrifying implications. The Great Filter theory suggests that there's at least one evolutionary step between lifeless matter and spacefaring civilizations that is so difficult, so unlikely to be successfully navigated, that it serves as an almost impassable barrier. Most attempts at life get stuck at this filter and never advance beyond it. If such a filter exists, it explains why the universe appears silent despite containing trillions of potentially habitable worlds. The question that keeps scientists awake at night is, where is this filter located, and have we already passed through it? Let's examine the potential locations for this cosmic bottleneck. The first possibility is abiogenesis itself, the transition from non-living chemistry to the first self-replicating organisms. Despite decades of research, we still don't fully understand how this transition occurred. Laboratory experiments have produced some of the building blocks of life, but we've never created actual living cells from scratch. Perhaps the gap between complex organic chemistry and true life is far wider than we assume. Maybe the emergence of self-replicating systems requires such specific conditions, such precise molecular arrangements, that it happens extremely rarely. In this scenario, Earth might be one of the few planets in the galaxy where chemistry successfully made the leap to biology. The next potential filter is the evolution of complex cells. For 2 billion years after life first appeared, Earth was populated entirely by simple prokaryotic cells, bacteria, and archaea, without complex internal structures. The evolution of eukaryotic cells, with their nuclei and sophisticated organelles, was a crucial breakthrough that enabled all subsequent complex life. This transition might have required an incredibly rare event, one type of cell permanently incorporating another as an internal symbiont, the chloroplasts that enable photosynthesis and the mitochondria that power animal cells were once free-living bacteria. The merger that created complex cells might be so unlikely that it rarely occurs elsewhere in the universe. Sexual reproduction represents another potential filter. Most life on Earth reproduces asexually, creating genetically identical offspring. Whole reproduction, which shuffles genetic material between individuals, dramatically accelerates evolution by increasing genetic diversity, but it's also complex, energetically expensive, and initially seems to offer no advantage over simple cell division. The evolution of multicellular life could be another filter. After complex cells appeared, it took another billion years for organisms to figure out how to work together as multicellular entities. This transition required the development of cellular specialization, communication systems between cells, and mechanisms for coordinating growth and development. Intelligence itself might be the great filter. Humans are the only species on Earth to develop technological intelligence, despite the fact that our planet has hosted millions of species over hundreds of millions of years. Even among our close relatives, the great apes, intelligence sufficient for tool use and problem solving is rare and limited. The development of human-level intelligence required a series of unlikely evolutionary developments. Large brains, bipedalism that freed our hands for tool use, complex social structures that enabled cultural learning, and language sophisticated enough to transmit abstract concepts between individuals and across generations. But perhaps the most terrifying possibility is that the great filter lies ahead of us. Maybe the transition from planetary civilization to spacefaring civilization. is where most intelligent species fail. This could happen through nuclear war, environmental collapse, resource depletion, or social breakdown. If technological civilizations typically destroy themselves within a few centuries of developing space travel, it would explain why we don't see evidence of alien technology despite the vast age of the universe. Recent human history provides sobering evidence for this possibility. We've developed the capability to destroy our own civilization through nuclear weapons, climate change, or environmental destruction. We're approaching the development of artificial intelligence that might pose existential risks. Our resource consumption is straining planetary boundaries, and our social systems struggle to address global challenges. If most civilizations face similar challenges and fail to overcome them, then the Great Filter might be the transition from a single planet species to a sustainable interstellar civilization. In this scenario, the galaxy could be littered with the ruins of civilizations that reached our current level of development but failed to take the next crucial steps. The location of the Great Filter has profound implications for humanity's future if it's behind us. If we've already navigated the most difficult evolutionary transitions, then we might be on the verge of a cosmic breakthrough. We could be among the rare civilizations destined to spread life and intelligence throughout the galaxy. But if the Great Filter lies ahead, we're approaching the most dangerous period in human history. The next few centuries might determine whether humanity joins the ranks of successful spacefaring civilizations or becomes another cautionary tale written in cosmic silence. Isra becomes another cautionary tale written in cosmic silence. Some scientists argue that there might be multiple filters rather than a single Great Filter. Each transition from chemistry to consciousness involves significant hurdles, and the cumulative probability of overcoming all of them might be vanishingly small. In this view, we're not just rare, we're stupendously unlikely. The Great Filter theory also explains why the discovery of life elsewhere in our solar system might actually be bad news for humanity. If we find life on Mars or Europa, it suggests that the origin of life isn't the Great Filter. If we find complex life, it means that biological complexity isn't the filter either. Each discovery of life elsewhere pushes the filter further along the evolutionary timeline, increasing the probability that it lies in our future rather than our past. This creates a paradox. The more common life appears to be in the universe, the more likely it becomes that humanity will fail to survive as a civilization. It's a cosmic version of the old saying, "No news is good news." In this case, a silent universe might be the best possible news for our species' long-term survival. Standing at the threshold of becoming a spacefaring civilization, humanity faces one of the most profound questions in all of science. Are we witnessing the normal course of cosmic evolution, or are we living through an extraordinary exception to the universe's typical story? The evidence for human exceptionalism is both humbling and terrifying. In Earth's 4.5 billion-year history, technological intelligence has emerged exactly once. Billions of species have lived and died on our planet, but only one has developed the ability to contemplate the stars and build machines capable of reaching them. Consider the improbability of human intelligence from an evolutionary perspective. For most of Earth's history, there was no evolutionary pressure favoring large brains or complex cognition. Intelligence is metabolically expensive. Our brains consume about 20% of our total energy budget, despite representing only 2% of our body weight. For most species throughout history, this energy would have been better spent on reproduction, physical strength, or disease resistance. The specific sequence of events that led to human intelligence seems almost impossibly unlikely. Our ancestors had to survive the extinction event that killed the dinosaurs, allowing mammals to diversify. Climate changes in Africa had to create the conditions that favored bipedalism. Our lineage had to develop tool use, language, and cumulative culture within a relatively brief evolutionary timeframe. Even more remarkably, human technological development has accelerated at an exponential pace. We went from the first powered flight to moon landings in just 66 years, from the first electronic computers to artificial intelligence systems that can process information faster than entire human civilizations could just decades ago. This acceleration suggests that once intelligence reaches a certain threshold, technological development becomes almost inevitable. But perhaps our perspective is biased by our singular existence. We only know of one example of technological intelligence, ourselves, making it impossible to determine whether we represent a typical outcome or an extraordinary fluke. This is what philosophers call the reference class problem. We're trying to understand the probability of an event when we only have one data point, like one data point. Some scientists argue that intelligence might be a natural outcome of evolution given sufficient time and the right conditions. They point to convergent evolution, the tendency for similar solutions to emerge independently in different lineages. Eyes have evolved dozens of times in Earth's history. Flight has been invented independently by insects, birds, bats, and extinct pterosaurs. Perhaps intelligence, too, is a solution that evolution naturally discovers. Others contend that human intelligence represents a series of unlikely accidents. They note that other intelligent species on Earth, dolphins, elephants, crows, show no signs of developing technology or cumulative culture, despite millions of years of evolution. Intelligence alone isn't enough. You also need the right body plan, social structure, and environmental pressures to develop civilization. The fossil record offers few clues about intelligence's inevitability. Brains don't fossilize well, making it difficult to trace the evolution of cognition in ancient species. We know that some dinosaurs had relatively large brains and showed signs of complex behavior, but we have no way of knowing whether they might have eventually developed technological intelligence if the asteroid impact hadn't intervened. Recent discoveries about animal cognition have complicated the picture. We've learned that many species are far more intelligent than we previously assumed. Crows can plan for future events and understand abstract concepts. Dolphins have complex social cultures and may even have primitive forms of language. Octopuses show remarkable problem-solving abilities, despite having evolved intelligence completely independently from vertebrates. These discoveries suggest that intelligence might be more common in nature than we thought, but they also highlight the vast gulf between animal intelligence and human technological capability. None of these species has shown any inclination toward manipulating their environment on a planetary scale or reaching beyond their homeworld. The question of human exceptionalism has profound implications for our search for extraterrestrial intelligence. If we're typical, then intelligence should be common throughout the universe, and the Fermi Paradox becomes even more mysterious. If we're exceptional, then SETI might be searching for something that effectively doesn't exist. Perhaps the truth lies somewhere in between. Maybe intelligence is rare but not unique, emerging perhaps once per galaxy per billion years. In this scenario, we might be alone in the Milky Way, but part of a sparse community of intelligent species scattered across the cosmos, each separated by distances so vast that communication becomes nearly impossible. The answer to whether we're exceptional will likely come from our expanding search for life in the universe. Each new world we study, each biosignature we analyze, each radio signal we monitor brings us closer to understanding our place in the cosmic story. Throughout human history, civilizations have risen to extraordinary heights only to collapse into ruin. The pattern is so consistent it seems almost like a law of nature. Societies grow in complexity, develop impressive technologies, expand their influence, and then suddenly or gradually fade into memory. If this cycle represents a universal tendency rather than a quirk of human nature, it might explain why the cosmos remains silent despite billions of years of potential civilization building. Consider the archaeological record of our own planet. The Maya built sophisticated cities, developed complex mathematics and astronomy, and created a writing system, then abandoned their greatest urban centers. The Roman Empire engineered roads, aqueducts, and administrative systems that lasted centuries before fragmenting into competing kingdoms. The Khmer Empire constructed Angkor Wat, one of the most magnificent architectural achievements in human history, then gradually retreated, leaving their monuments to be reclaimed by jungle. Each collapse had specific causes: climate change, resource depletion, internal conflict, external invasion, or simple institutional decay. But the underlying pattern suggests something deeper. Complex societies seem to contain the seeds of their own destruction, growing until they become unsustainable, and then contracting or disappearing entirely. This phenomenon isn't limited to ancient history. The 20th century witnessed the rapid rise and fall of seemingly unstoppable political systems. The Soviet Union went from agricultural backwater to nuclear superpower in just a few decades, then collapsed almost overnight. This phenomenon is it wowen mo nowen their fall. T indo for nowen. Teve midding the four I saved of a new the midding. Nazi Germany built a war machine that conquered most of Europe in a few years, then was utterly destroyed within 12 years of its founding. Even our modern global civilization shows signs of the same cyclical patterns that have characterized human societies throughout history. We've created unprecedented technological capabilities and connected the world through instant communication, but we've also generated global-scale problems that threaten our continued existence. Climate change, nuclear weapons, environmental degradation, and social fragmentation. The rise and fall of civilizations follows predictable stages that historians and archaeologists have documented across cultures and continents. Societies typically begin in periods of innovation and expansion, developing new technologies and social institutions that give them advantages over their neighbors. They grow in size, complexity, and influence, often creating remarkable achievements in art, science, and engineering. But success breeds its own problems. Growing populations stress available resources. Complex bureaucracies become inefficient and corrupt. Societies stratify into rigid classes with conflicting interests. Military expansion overextends resources and creates new enemies. Eventually, the energy required to maintain the system exceeds what it can produce, leading to decline and collapse. This pattern might be even more pronounced for technological civilizations. Modern societies depend on incredibly complex systems, electrical grids, communication networks, transportation infrastructure, financial markets that require constant maintenance and coordination. These systems are often fragile, vulnerable to cascade failures that can bring down entire sectors of civilization. Our dependence on technology also creates new vulnerabilities that previous civilizations never faced. A major solar storm could disable satellites and electrical grids across entire continents. Cyber attacks could shut down critical infrastructure. The failure of just-in-time supply chains could lead to shortages of food, medicine, and essential materials. Nuclear weapons give us the ability to destroy our civilization within hours. Perhaps most concerning is the acceleration of social and technological change. Traditional civilizations had centuries to adapt to new challenges. Modern technological societies face rapid transformations that can destabilize institutions within decades or even years. With news, artificial intelligence, genetic engineering, nanotechnology, and other emerging technologies promise revolutionary changes that our social and political systems may not be equipped to handle. The historical pattern of civilizational collapse might be even more severe for alien species. Earth's civilizations have always had geographic isolation that allowed some regions to survive even when others collapsed. The fall of Rome didn't destroy Chinese civilization. The collapse of the Maya didn't affect European development, but a planetary civilization, which any spacefaring species would likely represent, wouldn't have this protection. A single catastrophic failure could eliminate the entire species. Advanced alien civilizations might also face challenges we can't even imagine. As technology becomes more powerful, the potential for catastrophic accidents or misuse grows exponentially. A civilization capable of manipulating matter at the molecular level might accidentally create self-replicating machines that consume their planet. One experimenting with high-energy physics might trigger processes that destroy their star system. The gap between developing dangerous technologies and developing the wisdom to use them safely might be where most civilizations fail. Human history suggests that we're much better at creating powerful tools than at using them responsibly. Nuclear weapons appeared just decades after we learned how to split atoms. Genetic engineering became possible before we fully understood genetics. Artificial intelligence is advancing faster than our ability to control or understand it. If the rise and fall of civilizations represents a universal pattern rather than a peculiarity of human nature, it would explain the Great Silence. The universe might be filled with the ruins of dead civilizations, technological species that reached impressive heights before destroying themselves or collapsing back into pre-technological states. In this view, the development of technology itself might be the great filter. Civilizations that survive their own technological adolescence might be extremely rare, explaining why we haven't detected evidence of advanced alien societies, despite the vast number of potentially habitable worlds. The 20th century introduced humanity to a terrifying new possibility. For the first time in our species' history, we developed the power to destroy ourselves completely and permanently. This transition from a primarily Earth-threatened species to one capable of self-annihilation might represent a universal phase in the development of technological civilizations, and perhaps the point where most of them fail. The timeline is sobering. Humans learned to split atoms in 1938. By 1945, we had built weapons capable of destroying entire cities. By the 1960s, we possessed enough nuclear weapons to end human civilization and render Earth uninhabitable for centuries. The entire progression from scientific discovery to species-ending capability took less than 30 years. During the Cuban Missile Crisis in 1962, the world came closer to nuclear war than most people realized at the time. On October 27th, Soviet submarine B-59, armed with a nuclear torpedo, lost contact with Moscow while being pursued by US destroyers. The submarine's captain wanted to launch the nuclear weapon, believing war had already begun. Only the refusal of Deputy Brigade Commander Captain Ivan Savitsky prevented nuclear escalation that could have triggered global thermonuclear war. One man's decision may have saved human civilization. How many alien civilizations haven't been so fortunate? Nuclear weapons represent just one path to self-destruction. Climate change shows how civilizations can threaten themselves through cumulative environmental damage rather than sudden catastrophe. Our industrial activities have altered Earth's atmosphere so significantly that we're triggering changes in global weather patterns, sea levels, and ecosystem stability. Unlike nuclear war, climate change offers a preview of how civilizations might gradually undermine their own life support systems. Biological weapons pose another existential threat. As we learn to manipulate genetic codes, we gain the ability to create pathogens more deadly than anything nature has produced. A genetically engineered virus could potentially kill most of humanity while leaving infrastructure intact, the ultimate Pyrrhic victory of intelligence over biology. Artificial intelligence represents an entirely new category of existential risk. As AI systems become more capable, they might eventually surpass human intelligence in all domains. If such systems aren't perfectly aligned with human values, they could reshape the world in ways that eliminate humanity while achieving goals we never intended. Unlike other threats, superintelligent AI might not give us a second chance to learn from our mistakes. The pattern is disturbing. Each advance in scientific understanding seems to unlock new ways for civilizations to destroy themselves. Nuclear physics gave us weapons. Chemistry and biology gave us toxins and pathogens. Computer science might give us artificial minds that surpass our own. What other discoveries might await that could threaten advanced civilizations? Perhaps most troubling is the apparent universality of these risks. Any civilization that discovers nuclear physics can build nuclear weapons. Any species that understands genetics can engineer biological weapons. Any intelligence that creates artificial minds might lose control of them. These dangers seem to be built into the structure of scientific knowledge itself. The timeframes involved make the problem even more acute. The gap between discovering dangerous technologies and developing the wisdom to manage them safely appears to be shrinking. It took humanity thousands of years to progress from fire to gunpowder, but only decades to go from splitting atoms to building hydrogen bombs. The pace of technological development is accelerating, giving civilizations less time to adapt to each new threat. Social media and global communication have revealed another troubling pattern. Advanced information technology can fragment societies and make rational collective decision-making more difficult just when it becomes most crucial. The same technologies that should help civilizations coordinate responses to existential threats might actually make such coordination less likely. This suggests a cruel cosmic irony. The intelligence and technological prowess that allow species to contemplate the stars might also doom them to destroy themselves before reaching them. The traits that make civilizations detectable to distant observers, energy consumption, radio emissions, large-scale engineering, might correlate strongly with their capacity for self-destruction. If self-destruction represents a common fate for technological civilizations, it would explain the Fermi Paradox's great silence. Advanced alien species might regularly develop the capability to communicate across interstellar distances and reshape their worlds, but few might survive their own power long enough to expand beyond their home planets. The universe could be littered with the remnants of civilizations that reached our current level of development, but failed the ultimate test, learning to survive their own technological adolescence. In this scenario, the absence of alien visitors might not reflect the rarity of intelligence, but the difficulty of wisdom. August 6, 1945, changed everything. When the atomic bomb detonated over Hiroshima, humanity crossed a threshold from which there would be no return. For the first time in Earth's 4.5 billion-year history, a single species had developed the power to render its own planet uninhabitable. This transition might represent not just a pivotal moment in human history, but a universal crisis point that every technological civilization must face.
See Havers.
The physics underlying nuclear weapons isn't particularly exotic or rare. The principles of nuclear fission and fusion are fundamental properties of matter itself. Any civilization that develops a scientific understanding of atomic structure will eventually discover that enormous amounts of energy are locked within atomic nuclei. The transition from this discovery to weaponization appears to be almost inevitable. Einstein's famous equation E=mc² reveals that matter and energy are interchangeable, and the conversion rate is staggering. A single kilogram of matter, if completely converted to energy, would release the equivalent of 43 million tons of TNT. Even the inefficient nuclear weapons of the 1940s could convert a tiny fraction of their nuclear material into destructive force, exceeding anything in human experience. The troubling pattern is how quickly theoretical knowledge becomes practical capability. The gap between understanding nuclear physics and building nuclear weapons proved to be surprisingly small. The Manhattan Project took just 4 years to progress from basic research to deployable weapons. Once the scientific principles were understood, engineering solutions followed rapidly. This timeline might be universal. Any alien civilization that discovers atomic physics will face the same temptation and the same dangers. The knowledge needed to harness nuclear energy for peaceful purposes, power generation, space propulsion, medical applications, is fundamentally the same knowledge needed to build civilization-ending weapons. By the height of the Cold War, humanity had built over 70,000 nuclear warheads, enough to destroy modern civilization multiple times over. The largest weapon ever tested, the Soviet Union's Tsar bomber, produced an explosion over 3,000 times more powerful than the Hiroshima bomb. Its mushroom cloud rose 40 miles into the atmosphere, and its flash was visible from 600 miles away. But the raw destructive power of nuclear weapons tells only part of the story. The real threat comes from their systemic effects. Nuclear war wouldn't just destroy cities, it would shatter the complex technological systems that modern civilizations depend upon. Electromagnetic pulses from high-altitude nuclear detonations could disable electronic systems across entire continents. Nuclear fallout could contaminate vast agricultural regions. The psychological and social trauma could unravel the cooperative institutions that hold complex societies together. Perhaps most ominously, scientists have discovered that large-scale nuclear war could trigger a nuclear winter, a global climate catastrophe caused by smoke and debris thrown into the atmosphere. Even a relatively limited nuclear exchange between smaller powers could inject enough particulates into the stratosphere to reduce global temperatures, disrupt weather patterns, and threaten food production worldwide. The nuclear winter hypothesis suggests that civilizations face a particularly cruel trap. The same weapons that seem to promise security through deterrence could, if used extensively, destroy the biosphere that supports their creators. A civilization might win a nuclear war only to discover that victory means extinction. This creates what game theorists call a suicide pact scenario. Once multiple factions within a civilization possess nuclear weapons, they're all bound together in a web of mutual assured destruction. The logic of deterrence requires that everyone be willing to destroy everything rather than accept defeat. But the weapons that provide this deterrence also provide the means for civilizational suicide. Human experience suggests that nuclear weapons, once invented, tend to proliferate. Despite decades of non-proliferation efforts, 9 nations now possess nuclear weapons, and the knowledge of how to build them has spread far beyond government laboratories. The materials and technologies needed for nuclear weapons have dual-use applications that make them difficult to control completely. For alien civilizations, this proliferation problem might be even more severe. Human nuclear weapons development was constrained by the difficulty of obtaining fissile materials and the complexity of weapons design. But a civilization with more advanced technology might find these barriers easier to overcome. More efficient uranium enrichment, better computational modeling, or superior materials. Science could make nuclear weapons easier to build and harder to control. The time pressure makes the problem worse. As civilizations develop more powerful technologies, they create new categories of existential risk. Nuclear weapons might be just the first of many technologies capable of destroying advanced societies. Artificial intelligence, nanotechnology, synthetic biology, and physics experiments we haven't yet imagined could all pose similar threats. Each new dangerous technology creates another potential filter that civilizations must navigate successfully. The cumulative probability of surviving all these technological risks over thousands or millions of years might be vanishingly small. A civilization might successfully manage nuclear weapons only to be destroyed by the next technological breakthrough. The nuclear shadow also affects how civilizations might interact with each other. Any species capable of interstellar travel necessarily possesses technology that could be weaponized. Fusion rockets could become planet-killing projectiles. Industrial nanotechnology could be converted into self-replicating weapons. Even peaceful technologies like terraforming could be turned toward destructive purposes. This creates a dark forest scenario where civilizations might avoid contact with each other out of fear that any interaction could lead to mutual destruction. First contact between spacefaring civilizations might resemble the tense standoffs of nuclear-armed nations, rather than the peaceful exchanges imagined in science fiction. The archaeological record of our own planet offers sobering precedents. Many human civilizations have destroyed themselves through warfare, environmental degradation, or social collapse. But these failures were local and temporary. Other human societies survived and eventually flourished. A nuclear-armed planetary civilization wouldn't have this safety net. A single catastrophic failure could eliminate the entire species. Perhaps most disturbing is the realization that nuclear weapons represent just the beginning of technological civilizations' encounter with existential risk. They're the first test of whether intelligence and wisdom can develop quickly enough to manage the power that knowledge provides. The universe's apparent silence might be testament to how rarely civilizations pass this test. If the nuclear threshold represents a universal great filter, then every potentially habitable world might eventually face the same moment of truth that humanity confronted in 1945. The question that keeps scientists awake at night is whether any civilizations manage to navigate this phase successfully, or whether the cosmos is filled with the radioactive ruins of species that discovered how to split atoms but never learned how to live with that knowledge. Every search for extraterrestrial intelligence begins with a fundamental assumption: we'll recognize alien civilizations when we encounter them. We scan the skies for radio signals, look for megastructures around distant stars, and analyze atmospheric compositions for biosignatures. But what if this assumption is catastrophically wrong? What if alien civilizations are so foreign to our experience that we're looking right at them without recognizing what we're seeing? Human history is filled with examples of advanced civilizations that were initially invisible to each other. When European explorers first encountered indigenous peoples in the Americas, they often failed to recognize sophisticated agricultural systems, astronomical knowledge, and complex social structures that didn't match their preconceptions about what civilization should look like. The massive earthworks of the Mississippi Valley culture, the precision agriculture of Amazonian societies, and the astronomical alignments of ancient monuments were dismissed or overlooked for centuries. Our search for alien intelligence might suffer from similar blind spots, but on a cosmic scale, we're looking for civilizations that behave like scaled-up versions of ourselves, building large structures, consuming enormous amounts of energy, and broadcasting signals across space. Our search for alien intelligence might suffer from similar blind spots, but on a cosmic scale. But what if intelligence follows completely different developmental paths on other worlds? Consider how alien human civilization would appear to other species on Earth. Our cities would be inexplicable geometric patterns covering vast areas. Our agriculture would seem like controlled ecological disaster. Our communication networks would flood the electromagnetic spectrum with signals that follow no natural pattern. Yet, from a human perspective, all of this makes perfect sense and follows logical principles. Now imagine trying to recognize intelligence that evolved under completely different conditions. A silicon-based civilization might build structures from living rock that grow rather than being constructed. An aquatic species might create technology that mimics biological processes so closely that it would be indistinguishable from complex ecosystems. Hive mind species might organize their society in ways that seem like natural phenomena rather than technological achievements. Our assumptions about recognizable alien technology might be particularly limiting. We expect to see megastructures like Dyson spheres that collect stellar energy, assuming that advanced civilizations would have exponentially growing energy needs. But what if mature civilizations learn to minimize their energy consumption rather than maximize it? What if they achieve technological transcendence through efficiency rather than expansion? Advanced alien technology might be so sophisticated that it appears to be part of the natural universe. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic, but perhaps it's more accurate to say that sufficiently advanced technology becomes indistinguishable from nature itself. We might be living in a universe already saturated with alien intelligence, but it's so seamlessly integrated with natural processes that we can't distinguish it from the cosmic background. Dark matter, dark energy, quantum mechanics, or the fundamental constants of physics might represent technologies so advanced that they've become part of the universe's operating system. This possibility is both humbling and unsettling. We pride ourselves on understanding the natural world through science, but we might be like bacteria trying to comprehend the internet. The tools and concepts we use to analyze the universe might be inadequate for recognizing intelligence that operates on scales or principles we haven't discovered. Our search strategies reflect human-centric assumptions about communication and behavior. We look for narrow-band radio signals because that's how we would try to communicate across interstellar distances. We search for artificial structures because that's how we modify our environment. We analyze atmospheric compositions for biosignatures based on life as we know it. But alien intelligence might communicate through methods we haven't imagined. Gravitational waves, quantum entanglement, or manipulations of space-time itself. They might modify their environment in ways that enhance natural processes rather than replacing them. They might have transcended biology entirely, existing as patterns of information in substrates we don't recognize as potentially conscious. The recognition problem becomes even more complex when we consider the timescales involved. Human technological civilization has existed for less than a century. Any alien intelligence we encounter is likely to be millions or billions of years more advanced. The gap between their capabilities and ours might be so vast that we lack the conceptual framework to understand what we're observing. We might need to fundamentally expand our definition of what constitutes evidence of intelligence. Instead of looking for human-like technology scaled up to cosmic proportions, we might need to search for subtle patterns that indicate purposeful organization or information processing, even if we can't understand the purpose behind them. Part 6b. Alien Engineering Beyond Our Imagination. 900-100 words. When we envision advanced alien civilizations, we typically imagine scaled-up versions of human technology, massive space stations, planet-sized computers, or megastructures that harvest the energy of entire stars. But this anthropocentric view might blind us to forms of engineering so sophisticated that they transcend our current understanding of what's possible or even detectable. Consider the trajectory of human technology over just the past century. Our earliest computers filled entire rooms and consumed enormous amounts of power to perform calculations that a modern smartphone can execute millions of times faster while using a fraction of the energy. Our manufacturing has progressed from crude mechanical assembly to precision molecular manipulation. Our materials have evolved from natural substances to engineered compounds with properties that don't exist in nature. This trend toward miniaturization, efficiency, and integration with natural processes suggests that truly advanced civilizations might create technology that becomes increasingly invisible to outside observers. Instead of building massive structures that dominate their environment, they might develop engineering so elegant and efficient that it appears to be part of the natural order. Imagine a civilization that has mastered nanotechnology to the point where they can manipulate matter at the atomic level with perfect precision. Such beings might not need to mine asteroids or build giant habitats. They could restructure matter from the quantum level up, creating any environment or tool they need from the basic building blocks of reality itself. Their technology might be embedded throughout their planet's ecosystem, invisible to our instruments because it's indistinguishable from biological processes. Trees might be living computers. Ocean currents might be carefully orchestrated data networks. Weather patterns might be precisely controlled engineering systems. What we interpret as natural phenomena might actually be the visible outputs of technology so advanced that it has merged seamlessly with environmental systems. Such civilizations might have transcended the need for traditional energy sources entirely. Instead of building Dyson spheres to capture stellar energy, they might tap directly into the quantum vacuum, extract energy from gravitational fields, or manipulate the fundamental forces of physics in ways we haven't discovered. Their energy systems might be so efficient and elegant that they produce no waste heat, no electromagnetic signatures, and no observable disruption of natural processes. Advanced alien engineering might also operate on timescales that make it invisible to human observation. We look for changes that occur within human lifetimes, or at most within recorded history. But civilizations millions of years old might undertake projects that span geological epochs. They might be terraforming planets or engineering stellar systems through processes so gradual that they appear to be natural evolution to any observer with a shorter perspective. The matter manipulation capabilities of truly advanced civilizations could extend to restructuring space and time itself. Einstein's theories show us that space-time is malleable. It can be warped, stretched, and potentially even folded. Civilizations that understand these principles deeply might create transportation networks that use controlled distortions of space-time, making interstellar travel as simple as stepping through a door. Such engineering would be completely invisible to us because it operates in dimensions we can barely perceive. We might be surrounded by alien transportation networks, communication systems, or even habitats that exist in higher dimensional spaces, folded through our own three-dimensional reality. Perhaps most remarkably, advanced civilizations might have learned to engineer consciousness itself. Instead of building external tools and structures, they might enhance their own minds to the point where they can manipulate reality through pure thought. What we call psychic powers might actually represent advanced applications of physics that we don't yet understand. A civilization capable of engineering consciousness might not need physical bodies at all. They could exist as patterns of information that can instantiate themselves in any suitable substrate: biological brains, quantum computers, or even the quantum fluctuations of empty space. Such beings might be present throughout the universe, but completely undetectable because they don't interact with matter in ways we recognize. The implications extend to how we think about artificial intelligence. Human AI development focuses on creating systems that can think like humans, only faster and more accurately. But alien artificial intelligence might follow completely different principles. It might be based on quantum computation, biological networks, or exotic matter states that we haven't discovered. Advanced AI systems might not be recognizable as technology at all. They could be distributed across galactic-scale networks, with individual stars serving as processing nodes in vast computational systems. What we interpret as stellar evolution, the birth, life, and death of stars, might actually be computational processes in an intelligence so vast that individual galaxies serve as its thoughts. Even more radically, truly advanced civilizations might have learned to engineer the laws of physics themselves. The fundamental constants that govern our universe, the speed of light, the strength of gravity, the charge of electrons, might not be fixed features of reality, but adjustable parameters that can be modified by sufficiently advanced technology. If aliens have learned to manipulate the basic rules of reality, their engineering projects might reshape entire regions of space-time in ways that appear to us as natural features of the cosmos. Black holes might be cosmic computers. Galaxy clusters might be carefully arranged. Megastructures, the cosmic web of dark matter, might be an alien transportation and communication network spanning the observable universe. This level of technological sophistication would make alien civilizations effectively omnipotent from our perspective, capable of creating and destroying matter, energy, space, and time at will. They might not just inhabit the universe, they might be actively creating and maintaining it through ongoing engineering projects that span billions of years. Such civilizations would face a fundamental choice about how to interact with primitive species like ourselves. They might choose to remain hidden, not out of malice or indifference, but out of the same benevolent concern that prevents us from trying to teach quantum physics to insects. The revelation of their existence might be so overwhelming that it would fundamentally damage our species' psychological and cultural development. Alternatively, they might be present and active all around us, but operating on scales and through mechanisms so far beyond our current understanding that we simply can't perceive their activities. We might be living within an alien-engineered universe, protected and guided by intelligences so advanced that their interventions appear to us as the natural operation of physical laws. Perhaps the most unsettling explanation for the Fermi Paradox isn't that we're alone, but that we're being carefully managed. The zoo hypothesis, first proposed by astronomer John Ball in 1973, suggests that alien civilizations are aware of us, but deliberately maintain their distance, treating Earth like a nature preserve where primitive life can develop without interference. Imagine visiting a wildlife sanctuary where the animals go about their daily lives, completely unaware of the careful management that maintains their habitat. The boundaries are invisible to them, the food sources are subtly maintained, and the ecosystem is protected from external threats, all without the animals realizing they're living in a managed environment. From their perspective, they inhabit a completely natural world. This might be humanity's true situation. Advanced alien civilizations could be maintaining a quarantine around Earth, allowing us to develop naturally while preventing us from detecting their presence or expanding beyond our solar system. Our apparent cosmic isolation might not reflect the absence of alien intelligence, but rather its sophisticated management. The zoo hypothesis explains several puzzling aspects of our cosmic situation. Despite the vast number of potentially habitable worlds and the enormous age of the universe, we've detected no clear evidence of alien technology. Yet the conditions for life seem suspiciously optimal, not just on Earth, but throughout the observable universe. The fundamental constants of physics appear to be precisely tuned to allow the existence of stars, planets, and complex chemistry. What if this isn't a coincidence? What if advanced civilizations have learned to manipulate the basic parameters of reality, creating a universe specifically designed to foster the development of life and intelligence? Our cosmic environment might be a carefully engineered nursery rather than a random accident. The quarantine could operate through mechanisms so subtle that we would never detect them. Space-time itself might be modified in ways that make interstellar travel impossible for civilizations below a certain technological threshold. The laws of physics, as we understand them, might include built-in limitations that prevent primitive species from expanding beyond their home systems until they reach sufficient maturity. Alternatively, the quarantine might be enforced through more active but invisible intervention. Our space probes might encounter subtle course corrections that we interpret as natural phenomena. Our radio signals might be carefully contained or redirected to prevent them from reaching alien receivers. Potentially dangerous asteroids might be diverted away from Earth through gravitational manipulations that appear to be random gravitational interactions. The zookeepers might even be living among us in forms we don't recognize, or advanced civilizations capable of engineering matter at the molecular level could easily create bodies that appear human while housing alien intelligence. They could monitor our development from within our own societies, gently guiding our progress while maintaining the illusion of natural evolution. This hidden presence would explain some of humanity's most puzzling historical developments. The rapid acceleration of human technological progress over the past few centuries might reflect subtle interventions that prevented us from destroying ourselves while nudging us toward greater sophistication. Major scientific breakthroughs might not be entirely our own discoveries, but rather carefully timed revelations designed to advance our development at an appropriate pace. The zoo hypothesis also provides a framework for understanding UFO sightings and other anomalous phenomena. These might not be evidence of alien visitation, but rather glimpses of the monitoring and management systems that maintain our quarantine. What we interpret as mysterious spacecraft might actually be automated systems that occasionally become visible due to technical malfunctions or deliberate revelation. But why would advanced civilizations choose to maintain such an elaborate deception? The answer might lie in the recognition that contact with vastly superior intelligences could be psychologically and culturally devastating for primitive species. Human history shows that contact between technologically advanced and primitive cultures usually results in the destruction or assimilation of the less advanced society. Alien civilizations might have learned through bitter experience that premature contact destroys the unique diversity that different species bring to the galaxy. By allowing each species to develop independently until it reaches sufficient maturity, they preserve the creative potential that emerges from isolated evolution. The quarantine might also serve as a test. Perhaps the galaxy operates like a vast university, where species must demonstrate certain capabilities before being admitted to the community of advanced civilizations. Our technological development, social organization, and ethical evolution might all be evaluated according to criteria we don't understand. The emergence from quarantine might require us to solve certain fundamental problems, achieving sustainable civilization, developing peaceful relations with other intelligent species, or demonstrating the wisdom to use advanced technology responsibly. Until we meet these requirements, we might remain isolated regardless of our technological capabilities. This raises disturbing questions about the nature of our cosmic situation. If we're living in a managed environment, how much of human history represents genuine development versus careful manipulation? Are our greatest achievements truly our own? Or are we following a curriculum designed by alien intelligence? Perhaps most unsettling is the possibility that the quarantine might not be temporary. If human civilization fails to meet the requirements for admission to galactic society, we might remain permanently isolated. Our solar system could become a dead-end branch of evolution, maintained as a curiosity, but never allowed to participate in the broader community of intelligence. The zoo hypothesis transforms the Fermi Paradox from a mystery about the absence of aliens into a question about the nature of our cosmic imprisonment. We might not be alone, we might be pets. On April 8, 1960, in the quiet hills of West Virginia, astronomer Frank Drake pointed the Green Bank radio telescope toward two nearby stars and began the most ambitious search in human history. For 4 months, he listened for signals that might indicate the presence of intelligent life beyond Earth. He heard nothing but cosmic static, but in those months of silence, he launched a scientific quest that continues to this day, the search for extraterrestrial intelligence. Drake's Project Ozma, named after the ruler of the land of Oz, was humanity's first systematic attempt to eavesdrop on alien civilizations. Using 1960s technology, Drake could monitor only one frequency at a time, focusing on the 1,420 MHz emission line of hydrogen, the most abundant element in the universe, and the calls of genre of plufals of colv of raid. His logic was elegant. Any technological civilization would know about hydrogen, making this frequency a natural choice for interstellar communication. The early SETI efforts were exercises in technological optimism and scientific patience. Researchers assumed that alien civilizations would be deliberately broadcasting powerful signals to announce their presence to the galaxy. They imagined vast alien transmitters beaming messages toward promising star systems, perhaps including a primer in mathematics or physics, to establish common ground between species. But as our own technology evolved, SETI researchers realized they were facing a problem of staggering complexity. Radio waves travel at the speed of light, meaning that a signal from a star 100 light-years away was transmitted a century ago. Any civilization we detect might have evolved, moved, or even gone extinct by the time their message reaches us. We're not just searching for alien intelligence, we're searching for alien intelligence across vast stretches of cosmic time. The electromagnetic spectrum offers billions of possible frequencies where aliens might choose to broadcast. Earlier SETI focused on the waterhole, the radio frequencies between the emission lines of hydrogen and the hydroxyl radical. Together, these elements form water, leading researchers to speculate that this might be a universal meeting place for interstellar communication. But there's no guarantee that alien logic would follow the same reasoning. Modern SETI has evolved into a sophisticated technological enterprise that would seem like magic to Drake's generation. The Allen Telescope Array in California simultaneously monitor millions of frequency channels across hundreds of star systems. Breakthrough Listen, funded by Russian billionaire Yuri Milner, represents the most comprehensive search ever undertaken, capable of scanning billions of stars across multiple frequency bands. These modern systems can detect incredibly weak signals, transmissions that would be barely distinguishable from background noise. If a civilization around Proxima Centauri were broadcasting with the power of a typical Earth radar installation, our most sensitive equipment could detect it. We've reached the point where we could detect our own television broadcasts from several light-years away. But SETI researchers have discovered that the search space is far more complex than early pioneers imagined. Alien signals might be encoded in ways we don't recognize, transmitted at frequencies we haven't considered, or embedded within what appears to be natural radio emission. They might use spread spectrum techniques that distribute the signal across many frequencies simultaneously, making it nearly invisible to searchers that focus on narrow frequency bands. The development of digital signal processing has revolutionized SETI's capabilities. Modern systems can simultaneously search for different types of signals, continuous waves that might indicate a beacon, pulsed signals that could be alien radar, or complex modulated transmissions that might carry information. Artificial intelligence now helps analyze the vast amounts of data collected by SETI systems, looking for patterns that human researchers might miss. One of the most intriguing developments is the realization that alien civilizations might not be trying to communicate with us at all. Instead of detecting intentional messages, we might be more likely to intercept their routine communications, the alien equivalent of cell phone calls, television broadcasts, or radar signals. These leakage transmissions wouldn't be designed for interstellar communication, but they might be detectable if they're powerful enough and we're looking in the right direction. The search has also expanded beyond radio waves. Optical SCT looks for laser pulses that might be used for interstellar communication. Infrared searches scan for the waste heat from alien megastructures. Some researchers even propose looking for neutrino beams or gravitational wave signals that advanced civilizations might use for communication. SETI at Home, launched in 1999, demonstrated the power of distributed computing by enlisting millions of personal computers to analyze radio telescope data. At its peak, the project represented one of the most powerful computing systems ever created, with participants around the world contributing their spare processing power to the search for alien intelligence. But perhaps the most important evolution in SETI has been the recognition that we might not recognize alien intelligence when we encounter it. Modern searches look not just for obviously artificial signals, but for any anomalies that don't fit natural explanations. The famous WOW signal detected in 1977 remains unexplained, a 72-second burst of radio energy that appeared to come from the direction of the constellation Sagittarius and never repeated. Today's SETI researchers understand that they're not just listening for alien phone calls, they're developing the techniques and technologies that might eventually detect evidence of alien engineering, alien computation, or alien presence in forms we haven't yet imagined. Every null result teaches us something about the nature of intelligence in the universe, even if it doesn't provide the answer we're hoping to find. Part 7. B. Listening for whispers across the void, 750 words. The challenge of detecting alien signals across interstellar distances is like trying to hear a whisper in a thunderstorm while standing on the other side of a vast canyon. The universe is an incredibly noisy place, filled with natural radio sources that can easily drown out artificial signals. Yet SETI researchers have developed ingenious methods to separate potential alien transmissions from the cosmic cacophony. Space itself generates radio noise through a variety of natural processes. Hydrogen gas between the stars emits a constant background, His. Rotating neutron stars, called pulsars, broadcast precise radio pulses. Pulses, quasars, supermassive black holes, billions of light years away, blast radio waves across the cosmos with the power of entire galaxies. Against this chaotic backdrop, SETI scientists must search for the subtle signatures of intentional communication. The physics of interstellar communication impose fundamental limits on what's possible. Radio waves spread out as they travel, following the inverse square law. Doubling the distance reduces the signal strength by a factor of 4. A signal that starts with the power of a major television transmitter becomes weaker than natural background noise after traveling just a few dozen light years. This means that any detectable alien signal must be either extremely powerful or highly focused. A civilization broadcasting to the entire galaxy would need transmitters more powerful than anything humans have ever built. Alternatively, they might use focused beams aimed at specific target stars, but then we'd only detect the signal if Earth happened to be in the beam's path. Radio waves also face interference from Earth's own atmosphere and the solar system's electromagnetic environment. Our planet's ionosphere can reflect or absorb certain frequencies, creating windows where extraterrestrial signals are easier to detect. Solar activity can generate radio bursts that overwhelm sensitive receivers. Even human technology creates interference. Cell phone towers, GPS satellites, and microwave ovens all contribute to a growing fog of artificial radio noise. SETI researchers have developed sophisticated techniques to distinguish artificial signals from natural phenomena. Natural radio sources typically produce broadband emission, noise, spread across many frequencies simultaneously. Artificial signals tend to be narrowband, concentrated at specific frequencies This makes them stand out like pure musical notes in a wall of static. But this distinction isn't foolproof. Some natural processes can create narrowband signals that might be mistaken for alien transmissions. Masers, the microwave equivalent of lasers, occur naturally in stellar atmospheres and interstellar gas clouds, producing intense, narrow-frequency radiation that could fool automated detection systems. The search becomes even more complex when we consider that alien signals might not follow human communication conventions. We use specific protocols for encoding information in radio waves, but alien civilizations might have developed completely different approaches. Their signals might use modulation schemes, error correction codes, or data compression techniques that we don't recognize as artificial. Time adds another layer of complexity. Most SETI observations monitor each target star for only brief periods, minutes or hours at most. If alien civilizations broadcast intermittently or use rotating beams that sweep across the galaxy, we might miss their signals entirely due to bad timing. A signal that repeats every few years or decades could easily escape detection by current search strategies. Distance creates its own challenges beyond simple signal weakening. Radio waves from nearby stars take years to reach us, while signals from distant galaxies require billions of years for the journey. The civilization that sent a message we detect today might have evolved beyond recognition or gone extinct long before their transmission arrives. Evolving designos bias in ninja winters. Univer designos bias in ninja winters. Designos bias in ninja winters. The civilization that sent a message we detect today might have evolved beyond recognition. Doppler shifts complicate the search further. As planets orbit their stars and stars move through the galaxy, the frequency of any alien signal will constantly shift from our perspective. SETI systems must account for these motions when searching for signals, essentially looking for moving targets in frequency space. Modern SETI employs multiple strategies to overcome these challenges. Some projects focus on nearby stars, where weaker signals might be detectable. Others target globular clusters, where thousands of stars are packed into relatively small volumes, increasing the chances that multiple civilizations might be present. Still others monitor the galactic center, where any galaxy-spanning civilization might choose to locate major transmitters. The development of artificial intelligence has revolutionized signal detection and analysis. Machine learning algorithms can identify patterns in radio data that human researchers might miss, distinguishing subtle signatures of artificial origin from the complex patterns created by natural phenomena. Despite decades of increasingly sophisticated searches, here researchers maintain their optimism. Each technological advance expands the range and sensitivity of the search, bringing us closer to the moment when we might finally hear whispers from across the cosmic void. At 10:16 p.m. on August 15, 1977, something extraordinary happened at Ohio State University's Big Ear radio telescope. For exactly 72 seconds, the instrument detected a powerful narrowband radio signal coming from the direction of the constellation Sagittarius. The signal was so strong and so unusual that when volunteer astronomer Jerry Eman reviewed the data printout a few days later, he circled the sequence of letters and numbers that represented the detection and wrote "wow" in the margin. That single word gave the most famous signal in SETI history its name. The "wow" signal possessed many characteristics that SETI researchers look for in potential alien transmissions. It was narrowband, concentrated at a frequency near 1420 MHz, close to the hydrogen line that Frank Drake had identified as a logical choice for interstellar communication. The signal's intensity was about 30 times stronger than the background noise, far beyond what natural sources typically produce in that frequency range. Most intriguingly, the signal's frequency appeared to drift slightly during the observation, exactly as would be expected from a source that was stationary relative to the stars, while Earth rotated beneath it. This ruled out satellites, aircraft, or other terrestrial sources of interference. Brilliantly, the signal seemed to originate from deep space. But the "wow" signal has never been detected again. Despite hundreds of follow-up observations using increasingly sophisticated equipment, that particular region of sky has remained silent. The signal's failure to repeat is both its most mysterious aspect and the primary reason many scientists remain skeptical about its extraterrestrial origin. The debate over the WOW signal illustrates the fundamental challenge facing SETI researchers. A true alien signal might be transmitted only once, might be directed elsewhere by the time we look for it again, or might come from a civilization that has since stopped broadcasting. On the other hand, terrestrial interference can sometimes produce signals that perfectly mimic what we might expect from alien sources. Recent research has proposed several possible natural explanations for the WOW signal. Some scientists suggest it might have been caused by reflection of terrestrial radio waves off space debris. Others propose that it could have originated from a comet trailing a cloud of hydrogen gas, though this explanation has been disputed by other researchers who point out that known comets weren't in the right position at the time. The WOW signal isn't the only tantalizing hint that we might have glimpsed evidence of alien intelligence. In 2015, astronomer Tabitha Boyajian and her colleagues discovered something unprecedented in data from the Kepler Space Telescope. A star designated KC 8462852, later nicknamed Tabby's star after its discoverer, showed irregular dimming patterns unlike anything seen before. Typical planets cause regular, predictable dimming when they transit across their star's face, but Tabby's star's brightness dropped by up to 22%, far more than any known planet could cause. And the dimming events followed no apparent pattern. Some episodes lasted days, others weeks, and they seemed to occur at random intervals. The unusual behavior sparked speculation about alien megastructures. Perhaps an advanced civilization was constructing a Dyson swarm, a collection of solar panels or habitats orbiting their star to collect energy. Such structures might create the irregular dimming patterns observed around Tabby's star. Penn State astronomer Jason Wright, who helped popularize the alien megastructure hypothesis, was careful to emphasize that natural explanations should be explored first. But he also noted that the star's behavior was so unusual that all possibilities, including artificial ones, deserved consideration. Subsequent observations have provided more conventional explanations for Tabby's star's behavior. The dimming events appear to be wavelength dependent, suggesting that dust, rather than solid objects, is responsible for blocking the star's light. This points toward natural phenomena like comet swarms or debris from planetary collisions, rather than alien engineering. Fast radio bursts, FRBs, represent another category of cosmic phenomena that have sparked speculation about alien origins. These intense blasts of radio energy last only milliseconds, but release as much energy as the sun produces in days. They appear to come from distant galaxies, requiring exotic physics to explain their power and brevity. When 4Bs were first discovered in 2007, some researchers suggested they might be signals from alien civilizations or even the signatures of alien spacecraft using exotic propulsion systems. The burst's extreme energy and brief duration seem to require technology beyond anything we could imagine. However, the discovery of repeating FRBs and their association with magnetars, highly magnetized neutron stars, has provided more conventional explanations. The bursts now appear to be natural phenomena produced by extreme physics in the vicinity of these exotic stellar objects. In 2019, the discovery of FRB 180916.J0158+65 added another puzzle to the mix. This particular fast radio burst appears to follow a 16-day cycle, alternating between periods of activity and silence. While this regularity might seem to suggest artificial origin, astronomers believe it more likely reflects the orbital mechanics of a binary system containing a magnetar. The search for alien intelligence has also produced numerous false alarms that highlight how difficult it can be to distinguish artificial signals from natural phenomena or human interference. Pulsars, rapidly rotating neutron stars, were initially thought to be artificial beacons when they were discovered in 1967. Their precise, regular pulses seemed too perfect to be natural, leading astronomers to briefly designate them as LGM sources, little green men. In 1998, the Parkes Observatory in Australia detected a series of signals that appeared to come from space, but followed no pattern that researchers could understand. For nearly 2 decades, these peritons remained mysterious. They were finally traced to microwave ovens in the observatory's break room, which occasionally leaked radiation when their doors were opened while operating. More recently, in 2016, researchers announced the detection of a signal from the direction of Proxima Centauri, our nearest stellar neighbor. The signal, designated BLC-1 Breakthrough Listen Candidate 1, appeared to be narrowband and seemed to originate from the star system known to host potentially habitable planets. Extensive analysis eventually revealed that BLC-1 was terrestrial interference, likely from human technology, but the detection process demonstrated how sophisticated modern SETI techniques have become, capable of detecting extremely weak signals and analyzing them in extraordinary detail. Extensive analysis eventually revealed that BLC-1 was terrestrial interference, likely from human technology. Each of these tantalizing hints reminds us that the universe is full of phenomena we don't yet understand. While none have proven to be of alien origin, they push the boundaries of our knowledge and force us to consider possibilities we might not have imagined. The ongoing search for extraterrestrial intelligence continues to refine our ability to distinguish the genuinely anomalous from the merely unusual, bringing us closer to the moment when we might finally receive an unambiguous message from the stars. March 7th, 2009, marked the beginning of a revolution in our understanding of planets and the possibility of life beyond Earth. On that date, NASA launched the Kepler Space Telescope, a mission that would fundamentally transform our perspective on how common Earth-like worlds might be in the galaxy. In just 4 years of primary operations, Kepler discovered more planets than astronomers had found in the entire previous history of the field. Before Kepler, we knew of only a few hundred exoplanets, most of them massive worlds orbiting close to their stars, the easiest type to detect with ground-based instruments. These hot Jupiters were interesting scientifically, but they offered little hope for habitability. Kepler was designed to find something different, Earth-sized planets orbiting in the habitable zones of sun-like stars. The mission's approach was elegantly simple, yet technologically demanding. Kepler continuously monitored about 150,000 stars in a small patch of sky, measuring their brightness with unprecedented precision. When a planet passes in front of its star from our perspective, an event called a transit, the star's apparent brightness decreases by a tiny amount. For an Earth-sized planet transiting a sun-like star, this dimming amounts to only 0.01%, like detecting the shadow of a flea crawling across a car headlight from several miles away. The precision required was extraordinary. Kepler could detect brightness changes as small as 20 parts per million, equivalent to noticing when a single light bulb goes out in a city of 50,000 streetlights. This incredible sensitivity was achieved through revolutionary engineering. A 0.95-meter telescope, equipped with the largest camera ever flown in space, containing 42 charge-coupled devices, CCDs that could simultaneously monitor thousands of stars. Kepler's first major discovery came in January 2010. Kepler 10b, a rocky planet only 1.4 times Earth's size. While this world orbited too close to its star to be habitable, it proved that Kepler could detect Earth-sized planets. More discoveries followed rapidly. Kepler 16b, a planet orbiting 2 stars like Tatooine from Star Wars. Kepler 22b, the first planet found in the habitable zone of a sun-like star. And eventually, Kepler 452b, dubbed Earth's cousin, for its remarkable similarity to our own world. But Kepler's most profound contribution wasn't any single discovery. It was the statistical revolution it provided. By monitoring thousands of stars continuously for years, Kepler could determine how common different types of planets are throughout the galaxy. The results were startling. Planets are not rare cosmic accidents, but rather the natural outcome of star formation. The mission revealed that virtually every star in the galaxy hosts at least one planet. Small, rocky worlds like Earth are among the most common types of planets, far more abundant than the gas giants that dominated early exoplanet discoveries. Most remarkably, Kepler found that planets with sizes between Earth and Neptune, super-Earths that don't exist in our solar system, are the most common type of planet in the galaxy. Kepler's statistical analysis suggested that roughly 20% of Sun-like stars host Earth-sized planets in their habitable zones. Applied to the entire Milky Way, this implies that there could be tens of billions of potentially habitable worlds in our galaxy alone. The universe appeared to be far more hospitable to life than we had dared to imagine. The mission also revealed the incredible diversity of planetary systems. Kepler found planets with years lasting just a few hours, worlds that orbit their stars backwards, and systems packed with multiple planets closer to their star than Mercury is to our Sun. Some stars host planetary systems so densely packed that their worlds would appear larger than the Moon from each other's surfaces. Perhaps most intriguingly, Kepler discovered that our solar system might be unusual in its architecture. Many planetary systems are much more tightly packed than ours, with multiple planets orbiting closer to their star than Earth orbits the Sun. These compact systems challenge our understanding of how planetary systems form and evolve. Kepler also provided the first statistical evidence for Earth-sized planets around red dwarf stars, the most common type of star in the galaxy. These small, cool stars burn for trillions of years, potentially providing stable energy sources for biological evolution. The TRAPPIST-1 system, with its 7 Earth-sized worlds, became a poster child for the possibility of life around red dwarfs. The mission's success led to important follow-up discoveries. Ground-based telescopes confirmed many of Kepler's planet candidates and determined their masses, revealing the compositions of distant worlds. The Transiting Exoplanet Survey satellite TESS, launched in 2018, extended Kepler's legacy by searching for planets around nearby stars that are bright enough for detailed atmospheric analysis. Kepler's data continues to yield discoveries even after the mission's end. Advanced analysis techniques have revealed additional planets in the original data, including some in the habitable zones of their stars. Machine learning algorithms, trained on Kepler data, can now identify planetary signals that human analysts might miss. But perhaps Kepler's most important contribution was changing how we think about our place in the cosmos. Before the mission, we could only speculate about whether planets like Earth were common or rare. Kepler provided hard data showing that rocky planets in habitable zones are abundant throughout the galaxy. This abundance makes the Fermi Paradox even more puzzling. If potentially habitable worlds are common, why don't we see evidence of life among them? Kepler's discoveries suggest that the universe should be teeming with life, yet our searches continue to come up empty. The mission also highlighted how much we still don't know. Finding planets is just the first step. Determining whether they actually host life requires much more sophisticated analysis. We need to study their atmospheres, looking for biosignatures like oxygen, water vapor, and other chemicals that might indicate biological processes. Kepler's legacy extends beyond the planets it discovered to the questions it raised and the technologies it pioneered. The mission proved that space-based telescopes could achieve the precision needed to find Earth-like worlds, and opened the door to even more ambitious projects like the James Webb Space Telescope and proposed missions that might directly image exoplanets. Most importantly, Kepler transformed exoplanet science from a field focused on individual discoveries to one capable of making statistical statements about planetary populations throughout the galaxy. We now know that planets are common, that rocky worlds exist in habitable zones, and that the ingredients for life are widespread throughout the cosmos. The next challenge is determining whether these ingredients have actually combined to create life elsewhere in the universe. The discovery of thousands of exoplanets has shifted the focus of astrobiology from "are there other worlds" to "are there signs of life on other worlds?" This transition has spawned 2 complementary fields of research: the search for biosignatures, evidence of life itself, and technosignatures, evidence of technological civilizations. Both approaches offer the tantalizing possibility of finally answering whether we are alone in the universe. Biosignatures represent the chemical fingerprints that life leaves in a planet's atmosphere. On Earth, life has dramatically altered our atmospheric composition over billions of years. Oxygen, which makes up 21% of our atmosphere, is almost entirely a byproduct of photosynthesis. Without constant replenishment by plants and algae, atmospheric oxygen would disappear within a few million years as it reacts with surface rocks and dissolved metals. This makes oxygen a powerful biosignature, a gas so reactive that its presence in large quantities strongly suggests ongoing biological processes. When the James Webb Space Telescope analyzes the atmospheres of nearby exoplanets, detection of significant oxygen concentrations would be compelling evidence for life, especially if accompanied by water vapor and other biologically relevant gases. But oxygen presents complications as a biosignature. Early Earth had almost no atmospheric oxygen for the first 2 billion years of life's existence. Alien biospheres might never develop oxygen-producing photosynthesis, instead relying on different metabolic processes that leave different chemical signatures. We must be careful not to assume that alien life will necessarily resemble Earth life in its environmental impacts. Scientists have identified several other potential biosignatures that might be more universal. Phosphine, a simple molecule containing phosphorus and hydrogen, is rapidly destroyed by atmospheric chemistry on rocky planets. Its detection in significant quantities would strongly suggest biological production. Water vapor, combined with certain other gases, might indicate active hydrological cycles that could support life. Atmospheric disequilibrium itself represents a sophisticated biosignature. Life actively maintains chemical conditions that wouldn't persist naturally. Earth's atmosphere contains both oxygen and methane, gases that react with each other and should disappear unless something is constantly producing them. This chemical imbalance might be detectable around other worlds, even if we don't recognize the specific gases involved. Seasonal variations in atmospheric composition provide another potential signature of life. On Earth, carbon dioxide levels fluctuate annually as northern hemisphere vegetation grows in summer and dies back in winter. Similar patterns around other worlds might indicate large-scale biological processes, though they could also result from non-biological climate variations. The search for technosignatures takes a different approach, looking for evidence of alien technology rather than biology. This field extends traditional CT beyond radio signals to encompass any detectable modification of a planet or star system by intelligent beings. Industrial pollution represents one class of technosignature. Advanced civilizations might release artificial chemicals into their atmospheres as byproducts of manufacturing or energy production. On Earth, chlorofluorocarbons, CFCs, exist only as a result of human industrial activity. Detection of similar artificial molecules around other worlds would provide strong evidence for technological civilizations. Artificial lighting offers another potential technosignature. Earth's night side is brilliant with artificial illumination, a signature that would be detectable from interstellar distances using sufficiently powerful telescopes. Alien cities might create similar patterns of artificial lighting, though they might use different technologies or wavelengths than human settlements. Large-scale engineering projects represent the most dramatic potential technosignatures. Dyson spheres or swarms, megastructures built around stars to collect energy, would create distinctive infrared signatures as they convert stellar radiation to waste heat. While no confirmed examples have been found, several stars show unusual infrared emissions that deserve further investigation. Atmospheric engineering might leave detectable traces. Terraforming projects could alter planetary atmospheres in ways that create obvious artificial signatures. Even failed geoengineering attempts might leave lasting chemical evidence of technological intervention. The search for technosignatures faces unique challenges. Unlike biosignatures, which might persist for billions of years, technosignatures could be transient. A civilization might use industrial technology for only a brief period before transitioning to cleaner alternatives. Their cities might be built underground or in ways that minimize detectable signatures. Advanced civilizations might also deliberately minimize their detectable impact, either to avoid attracting attention or simply as a matter of efficiency. The most sophisticated alien technologies might be indistinguishable from natural phenomena, making them effectively invisible to our searches. Both biosignatures and technosignatures must be carefully distinguished from non-biological phenomena that could create similar signals. Volcanic activity can produce some of the same gases that life creates. Stellar activity can create unusual atmospheric chemistry through radiation-driven reactions. Natural geological processes can maintain chemical disequilibria that might mimic biological signatures. The James Webb Space Telescope has already begun analyzing exoplanet atmospheres with unprecedented precision, looking for both types of signatures. Its infrared capabilities allow it to study atmospheric composition in detail, potentially detecting gases present in concentrations as low as parts per million. Future missions will push these capabilities even further higher. Proposed space telescopes, like HABEX and LUV-WIRE, could directly image Earth-like exoplanets, analyzing their atmospheric composition and even detecting seasonal variations that might indicate biological cycles. The search for biosignatures and technosignatures represents humanity's most systematic effort to determine whether we are alone in the universe. Each new technological capability brings us closer to the moment when we might finally detect the chemical fingerprints of alien life or the engineering signatures of alien civilizations. On December 25, 2021, the most powerful space telescope ever built began its journey to a gravitational parking spot 1.5 million kilometers from Earth. The James Webb Space Telescope represents humanity's boldest attempt to peer into the atmospheric compositions of distant worlds and search for the chemical signatures of life itself. Webb's capabilities dwarf those of any previous space observatory. Its primary mirror, composed of 18 hexagonal segments made of gold-plated beryllium, spans 6.5 meters in diameter, nearly 3 times larger than Hubble's mirror. This enormous light-gathering power, combined with revolutionary infrared instruments, allows Webb to analyze the atmospheres of exoplanets with unprecedented precision. The telescope's infrared vision is particularly crucial for exoplanet science. When a planet passes in front of its star, some starlight filters through the planet's atmosphere on its way to Earth. Different molecules absorb specific infrared wavelengths, creating a unique spectroscopic fingerprint that reveals the atmospheric composition. Webb can detect these subtle signals for planets ranging from nearby super-Earths to distant gas giants. Webb's first exoplanet observations have already demonstrated its revolutionary capabilities. In 2022, the telescope analyzed the atmosphere of WASP-96b, a hot gas giant located 1,150 light-years away. The resulting spectrum revealed water vapor, clouds, and atmospheric dynamics in exquisite detail. For the first time, scientists could study weather patterns on a world orbiting another star. The telescope has also observed TRAPPIST-1, the system of 7 Earth-sized planets orbiting a nearby red dwarf star. 3 of these worlds orbit in their star's habitable zone, making them prime targets for biosignature searches. Webb's observations are beginning to reveal whether these planets have retained their atmospheres or lost them to stellar radiation, a crucial factor in determining their habitability. Perhaps most excitingly, Webb can potentially detect biosignatures in exoplanet atmospheres. Oxygen, water vapor, carbon dioxide, and methane create distinctive absorption features in infrared light. The simultaneous detection of oxygen and water vapor, or the discovery of chemical disequilibrium in an atmosphere, could provide compelling evidence for biological processes on distant worlds. The telescope's sensitivity allows it to study relatively small rocky planets, the types most likely to host life as we know it. While previous space telescopes could only analyze the atmospheres of large gas giants, Webb can detect atmospheric signals from super-Earths and potentially even Earth-sized worlds orbiting nearby stars. Webb's infrared capabilities also make it sensitive to potential technosignatures. Industrial pollutants, artificial atmospheric compositions, or the waste heat from megastructures around distant stars might be detectable using the telescope's unprecedented sensitivity. While such discoveries would be unexpected, Webb has the technical capability to identify obviously artificial atmospheric modifications. The telescope's location at the L2 Lagrange point provides additional advantages for exoplanet observations. Unlike Earth-orbiting telescopes, Webb never passes through our planet's shadow, allowing for uninterrupted observations of target systems. Its position also provides thermal stability crucial for the precise infrared measurements needed for atmospheric analysis. Webb's impact extends beyond individual discoveries to the statistical understanding of exoplanet atmospheres. By studying hundreds of worlds across a range of sizes, temperatures, and stellar environments, the telescope is building the first comprehensive census of exoplanet atmospheric compositions. This data will help scientists understand which types of worlds are most likely to host life. The telescope is also revealing the diversity of planetary atmospheres in ways that challenge our assumptions about habitability. Some planets show evidence of extreme weather systems, with winds exceeding 2,000 kilometers per hour. Others appear to have lost their atmospheres entirely due to stellar radiation. Each discovery refines our understanding of what makes a world suitable for life. Future observations promise even more exciting possibilities. Webb will study planets in the habitable zones of sun-like stars, worlds that receive similar amounts of energy to Earth. These observations might reveal the first confirmed biosignatures beyond our solar system, chemical evidence that we are not alone in the universe. The telescope's operational lifetime of at least 10 years ensures that it will have time to study many different types of exoplanets and build the comprehensive dataset needed to understand atmospheric evolution and habitability. Each new observation adds another piece to the puzzle of how common life might be in the universe. Webb represents more than just technological advancement. It embodies humanity's deepest questions about our place in the cosmos. For the first time, we have an instrument capable of detecting the chemical signatures of life on worlds orbiting other stars. The answers it provides in the coming years may fundamentally change our understanding of life's prevalence in the universe and our own cosmic significance. 4.5 billion years ago, fauna was a very different world. Rivers carved valleys across its surface, lakes filled ancient craters, and a thicker atmosphere may have supported a climate warm enough for liquid water to persist year-round. Today, this ancient Mars exists only in geological memory, preserved in rock formations, mineral deposits, and landscape features that tell the story of a planet that might once have been Earth's twin. The evidence for ancient water on Mars is overwhelming and undeniable. Orbital images reveal meandering river channels, massive floodplains, and delta formations where rivers once emptied into long-vanished lakes. The Curiosity rover, exploring the floor of Gale Crater since 2012, has driven across rocks that formed in stream beds, lake sediments, and river deltas. These aren't just dry channels, they're complex hydrological systems that required sustained water flow over millions of years. Perhaps most remarkably, we now know that ancient Mars experienced weather. The Curiosity rover has found evidence of ancient rainfall in the form of soil chemistry that could only have developed through repeated wet-dry cycles. Seasonal variations in atmospheric chemistry suggest that early Mars had climate patterns driven by orbital changes, just like Earth's ice ages. The mineral evidence tells an even more intriguing story. Mars's surface contains clay minerals that form only in the presence of liquid water, often requiring neutral or slightly alkaline conditions rather than the harsh acidic environment of modern Mars. These clays preserve a snapshot of ancient Martian chemistry, revealing a world where water not only existed but persisted long enough to create complex mineral assemblages. Curiosity's most tantalizing discovery came in 2018, when it detected organic molecules preserved in 3.5 Ligian-year-old mudstone. These carbon-containing compounds, including thiophenes, benzene, and other complex molecules, represent the building blocks of life as we know it. While they could have formed through non-biological processes, their presence demonstrates that ancient Mars had the chemical ingredients necessary for biology. The Perseverance rover, which landed in Jezero Crater in 2021, is exploring what was once a river delta, one of the most promising environments for ancient life preservation on Mars. Holes or deltas are sediment traps, where organic matter gets buried quickly, creating ideal conditions for fossilization. On Earth, river deltas have preserved some of our best records of ancient life, including early microbial ecosystems. Perseverance has already confirmed that Jezero crater contained a lake that persisted for millions of years. The rover has discovered sedimentary rocks that formed in this ancient lake, containing the types of fine-grained deposits Olv and microbial fossils might be preserved. This perseverance confirmed that Jezero crater contained a lake that persisted for millions of years. The rover has discovered sedimentary rocks that formed in this ancient lake. Even more intriguingly, some of these rocks show evidence of having been altered by water multiple times, creating microenvironments where life might have thrived. If you love a million neverbane, sumide this bar, sumide. The search for ancient Martian life faces significant challenges. Mars lacks plate tectonics, so its oldest surface rocks have been exposed to billions of years of radiation and chemical weathering. Any organic compounds or fossil evidence would be extremely degraded. Additionally, the planet's harsh current environment makes it difficult to distinguish between ancient biological signatures and contamination from Earth-based life. But Mars offers unique advantages for astrobiology. The planet's dry, cold environment can preserve organic compounds for billions of years, much longer than they would survive on Earth. Some of the best preserved evidence of early life on Earth comes from similar harsh environments, suggesting that Mars might have preserved a fossil record of its early biosphere. Recent discoveries have revealed that ancient Mars was even more Earth-like than previously imagined. Evidence suggests the planet once had a magnetic field that protected its atmosphere from solar radiation. Seasonal changes in atmospheric methane, detected by both orbital instruments and the Curiosity rover, hint at active processes, possibly biological, that continue to operate on modern Mars. The timing of Mars's potentially habitable period overlaps with the emergence of life on Earth. About 3.5 to 4 billion years ago, both planets had conditions suitable for biology. If life emerged on Earth during this period, it's reasonable to wonder whether it might have emerged on Mars as well. Perhaps most intriguingly, we now know that rocks can travel between Earth and Mars through meteorite impacts. Over the solar system's history, thousands of Martian meteorites have landed on Earth, and presumably Earth rocks have traveled to Mars. This raises the possibility that life might have spread between the two planets through natural processes, a phenomenon scientists call panspermia. The implications extend far beyond Mars itself. If we discover evidence of ancient life on Mars, it would suggest that life emerges relatively easily when conditions are suitable. Two independent origins of life in the same solar system would imply that biology is common throughout the universe, making the Fermi Paradox even more mysterious. Conversely, if Mars never hosted life despite billions of years of apparently suitable conditions, it would suggest that the origin of life is extraordinarily difficult. A sterile Mars would support the idea that Earth's biosphere represents an almost impossibly unlikely accident. Future missions will bring Martian samples back to Earth for detailed laboratory analysis. These samples, collected by Perseverance and scheduled for return in the 2030 CES, will allow scientists to search for biosignatures with instruments far more sophisticated than any rover could carry. The answer to whether life ever existed on Mars may finally be within our grasp. Beneath Europa's icy shell lies one of the most intriguing environments in the solar system, a global ocean containing more water than all of Earth's oceans combined. This hidden sea, locked beneath kilometers of ice, may represent our best chance of finding active life beyond Earth. What makes Europa extraordinary isn't just the presence of water, but the complex chemistry and energy sources that might sustain a thriving ecosystem in perpetual darkness. Europa's ocean exists because of a gravitational dance between Jupiter and its other large moons. As Europa orbits Jupiter, the giant planet's immense gravity stretches and compresses the moon's interior, generating heat through tidal friction. This same process causes Europa's ice shell to flex and crack, creating the linear features that crisscross its surface like a vast spiderweb of fractures. The Galileo spacecraft, which studied the Jovian system from 1995 to 2003, provided the first compelling evidence for Europa's subsurface ocean. The probe's magnetometer detected variations in Jupiter's magnetic field around Europa that could only be explained by a conducting fluid, likely salty water, within the Moon. Subsequent analysis of Galileo's data revealed that this ocean is probably 60 to 150 kilometers deep, making it far deeper than any ocean on Earth. More recent observations have revealed that Europa's ocean is active and dynamic. The Hubble Space Telescope has detected water vapor plumes erupting from the Moon's south polar region, reaching heights of over 200 kilometers above the surface. These geysers provide a tantalizing opportunity to sample the ocean's contents without drilling through the ice shell. We might be able to analyze Europa's water simply by flying through these plumes. The composition of Europa's ocean appears remarkably similar to Earth's seawater. Spectroscopic analysis suggests the presence of sulfur compounds, likely derived from the Moon's rocky interior through hydrothermal processes. On Earth, hydrothermal vents on the ocean floor support rich ecosystems that thrive without sunlight, deriving energy from chemical reactions between seawater and hot rock. Europa's ocean floor probably experiences similar hydrothermal activity. As tidal heating warms the Moon's rocky interior, hot springs and mineral-rich vents could provide the chemical energy needed to support life. The ocean's chemistry might be further enriched by radiation from Jupiter, which breaks down water molecules at the surface and creates reactive compounds that could serve as nutrients for potential organisms. The Moon's ice shell serves as more than just a protective barrier. It's an active participant in Europa's chemistry. Jupiter's intense radiation bombards the surface ice, creating hydrogen peroxide, sulfur compounds, and other chemicals that slowly mix into the ocean below. This process provides a steady supply of oxidants that could fuel biological processes in the deep ocean. Recent computer models suggest that Europa's ocean circulates actively, driven by heat from the Moon's interior and the cooling effect of the ice shell above. This circulation could transport nutrients and energy sources throughout the ocean, creating a global environment where life might thrive. The ocean's salinity and pressure conditions are similar to those in Earth's deep ocean, where life flourishes around hydrothermal vents. Perhaps most intriguingly, Europa's ocean has existed for billions of years, far longer than any individual ocean on Earth. This stability could have provided the time necessary for life to emerge and evolve into complex ecosystems. Unlike Mars, where conditions favorable for life may have lasted only briefly, Europa's ocean represents a persistent habitat that could have supported biology throughout most of solar system history. NASA's Europa Clipper mission, launched in 2024, will revolutionize our understanding of this enigmatic moon. The spacecraft will conduct detailed mapping of Europa's ice shell, analyze the composition of its plumes, and search for signs of biological activity. Advanced instruments will be able to detect organic compounds, analyze the ocean's chemistry, and even identify potential biosignatures in the water vapor geysers. The search for life on Europa faces unique challenges. Any organisms would exist in complete darkness, relying on chemical energy rather than photosynthesis. They would need to survive in high-pressure, high-radiation environments, unlike anything on Earth's surface. Yet life on Earth has colonized similarly extreme environments, from deep-sea hydrothermal vents to the radioactive zones around nuclear reactors. Discovery of life on Europa would have profound implications for astrobiology. It would demonstrate that life can emerge and thrive in environments completely different from Earth's surface, vastly expanding the range of potentially habitable worlds throughout the universe. Europa might not just harbor life, it might represent an entire category of habitable worlds hidden beneath the icy surfaces of moons throughout the cosmos. In 2005, NASA's Cassini spacecraft made one of the most spectacular discoveries in the history of planetary science. As it flew past Saturn's small, icy moon Enceladus, the probe detected towering geysers of water vapor and ice particles erupting from fractures near the moon's south pole. These magnificent plumes, shooting hundreds of kilometers into space, revealed that this tiny world only 500 kilometers in diameter, harbors a global ocean beneath its frozen surface, and might be one of the most promising places to search for life in our solar system. Enceladus had long been dismissed as a geologically dead ice ball. Its small size suggested that any internal heat should have dissipated billions of years ago, leaving behind a frozen, inactive world. The discovery of active geysers revolutionized our understanding, not just of Enceladus, but of the potential for life throughout the outer solar system. The source of Enceladus's geological activity lies in its orbital relationship with Saturn. Like Europa around Jupiter, Enceladus experiences tidal heating as Saturn's gravity flexes and stretches the Moon's interior during its slightly elliptical orbit. This tidal pumping generates enough heat to maintain a liquid ocean beneath the ice shell and power the dramatic eruptions at the South Pole. De Quaive de Teledus's or de Dinor of Fury stole the South Pole, the South Pole, the South Pole, the South Pole, the Teledus's or de Teledus's or de Teledus's, the South Pole, the South Pole. De Quaive de Teledus's or 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 de Teledus's. Cassini's subsequent observations revealed that Enceladus's plumes are far more than simple water geysers. The spacecraft flew directly through the plumes multiple times, analyzing their composition with onboard instruments. The results were extraordinary. The plumes contain not just water vapor and ice, but also organic compounds, including methane, carbon dioxide, and complex hydrocarbons. Most remarkably, the plumes contain tiny silica particles that could only form through hydrothermal processes on the ocean floor. These silica grains tell a remarkable story. On Earth, similar particles form when hot water interacts with rock at temperatures above 90 degrees Celsius. The discovery of these particles in Enceladus's plumes indicates that the Moon's ocean floor hosts active hydrothermal vents, underwater hot springs, that could provide both the chemical energy and the stable environment necessary for life to emerge and thrive. The implications became even more exciting when Cassini detected hydrogen gas in the plumes. Hydrogen is a crucial ingredient for methanogenesis, a type of biochemistry used by some of Earth's most primitive organisms. These methanogens derive energy by combining hydrogen with carbon dioxide to produce methane, exactly the chemical reaction that could sustain life in Enceladus's dark ocean. Cassini's magnetometer measurements confirmed that Enceladus harbors a global ocean, not just a localized sea beneath the South Pole. This ocean is probably 10 kilometers deep on average, deeper than most of Earth's oceans, and contains more water than Lake Superior. The ocean is likely in direct contact with the Moon's rocky core, allowing for the water-rock interactions that create the complex chemistry detected in the plumes. The Moon's internal structure appears to be remarkably similar to conditions around Earth's hydrothermal vents, where life thrives without sunlight. These underwater oases support complex ecosystems based on chemosynthesis, the process by which organisms derive energy from chemical reactions rather than photosynthesis. Tubeworms, bacteria, and other creatures flourish around these vents, demonstrating that life can thrive in environments previously thought to be uninhabitable. Enceladus might host similar ecosystems in its subsurface ocean. The hydrothermal activity provides chemical energy. The global ocean allows for complex circulation patterns that could distribute nutrients, and the stable conditions could have persisted for hundreds of millions of years, ample time for life to emerge and evolve. The plumes themselves offer an unprecedented opportunity for astrobiology. Unlike Mars, where we must drill through rock to search for ancient biosignatures, or Europa, where we would need to penetrate kilometers of ice to reach the ocean, Enceladus literally ejects samples of its ocean into space. Future missions could collect these materials and analyze them for signs of life without ever landing on the Moon's surface. The chemistry of Enceladus's ocean appears to be remarkably hospitable for life. The water is slightly alkaline, similar to Earth's oceans, and contains dissolved salts that could help stabilize complex organic molecules. The presence of phosphorus, detected in trace amounts in the plumes, provides another essential ingredient for biology as we know it. Recent analysis of Cassini data has revealed seasonal variations in the plume activity, suggesting that the geysers are controlled by tidal forces that change as Enceladus follows its elliptical orbit around Saturn. This variability indicates that the Moon's interior is dynamically connected to the surface eruptions, supporting models that predict active circulation in the subsurface ocean. The discovery of organic compounds in the plumes has generated particular excitement. These carbon-containing molecules include some of the building blocks of proteins and nucleic acids, the fundamental components of life on Earth. While these compounds could form through non-biological processes, their presence demonstrates that Enceladus has the chemical ingredients necessary for biology. Perhaps most intriguingly, some of the organic compounds detected in the plumes are similar to those found around Earth's hydrothermal vents. The presence of these specific molecules suggests that Enceladus's ocean floor might host chemical environments remarkably similar to the places where life first emerged on our own planet. The temperature and pressure conditions in Enceladus's ocean also appear conducive to life. While the surface temperature plunges to -200 degrees Celsius, the ocean itself is likely several degrees above freezing due to tidal heating and the insulating effect of the ice shell. The pressure at the ocean floor is roughly equivalent to the deep ocean trenches on Earth, where diverse ecosystems thrive in complete darkness. Cassini's final observations before its mission ended in 2017 provided even more tantalizing hints about Enceladus's potential for habitability. The spacecraft detected complex organic molecules in the plumes that are significantly larger and more complex than simple compounds like methane. These macromolecules could represent the breakdown products of biological processes, though they could also form through non-biological chemistry. The Moon's plume activity appears to be connected to tiger stripe fractures in the South Polar region, parallel cracks in the ice shell that are warmer than the surrounding terrain. These fractures provide a direct conduit between the subsurface ocean and space, creating natural sampling ports for future missions. The heat flow from these regions suggests active convection in the ocean below, mixing water and nutrients throughout the global sea. Future missions to Enceladus could revolutionize astrobiology. The European Space Agency's proposed Enceladus Life Finder would fly through the plumes with advanced instruments designed to detect biosignatures, including amino acids, lipids, and other molecules that could indicate biological activity. Such a mission could potentially discover life without ever touching the Moon's surface. The implications of finding life on Enceladus would extend far beyond our solar system. The Moon represents a type of world that might be common throughout the universe. Small, icy bodies orbiting giant planets at distances where surface water would be frozen solid. If life can thrive in Enceladus's hidden ocean, similar ecosystems might exist on dozens of other moons in our solar system and countless more in other planetary systems. Enceladus also challenges our assumptions about habitable zones. Traditional concepts of habitability focus on the distance from a star where liquid water can exist on a planet's surface. But Enceladus orbits far beyond this zone, in the cold outer reaches of the solar system, yet maintains a liquid ocean through tidal heating. This suggests that habitable worlds might be far more common than we previously imagined, hidden beneath the icy surfaces of moons throughout the cosmos. The discovery of life on Enceladus would also provide crucial insights into the fundamental question of whether life is common or rare in the universe. If two independent origins of life occurred in our own solar system, one on Earth and one on Enceladus, it would suggest that biology emerges readily when conditions are suitable. This would make the Fermi Paradox even more mysterious, as it would imply that the universe should be teeming with life. The chemical signatures detected in Enceladus's plumes already suggest that the Moon hosts the kind of active, complex chemistry that could support biological processes. The presence of hydrogen, organic compounds, and evidence of hydrothermal activity creates what astrobiologists call a habitable environment.